Something terrible happened yesterday. I took tea break and I forgot to hit record afterwards, and I lost half the lecture. And I'm
just thought about this morning, and we did. Yeah, I forgot to remind you. Sorry.
That's okay. I think what I need to do. I mean, it's not your job; it's my job. The problem is there's so many things to think about that it's easy to forget to do that thing. I need sticky notes so I can put a sticky note in the center of the screen, so I can't even go forward unless I record. I will find sticky notes, but not right now. I didn't think to look for them. Okay, we're doing homework number, what is this, 3? 4?
3, yep, 3.
This is homework number 3. Ooh, this marker got a wee bit dried out. That's no bueno. Maybe I should dip it in my coffee. Oh, that is evil. Evil, evil dried out marker.
Did you leave the caps off all of them?
No, I had it in my pocket. You know, I think I went on a bike ride after class yesterday in the sun, and I don't know, I took my blazer, none of it made any sense, but I think I baked it dry.
Do you wear your blazer all summer?
Well, for teaching, yes. But no, I usually don't wear my blazer when I'm riding a bike. I wanted to get a falafel really bad or something, and I just went out the door, you know?
Yeah.
But honestly, I have been known to wear my blazer all summer. Recently, I've switched to sweaters, but I am just that much of a stiff. Okay. All right, so hold on. I think I've got another secret good one here. Secret good one. Here we go. Homework number 3. Yeah, here we go. That's jazz. This is chapter 4. And what are the numbers, Laura?
45, 47, 56, 57 D, E, and F, and 58 A, C, and D.
So I'll probably cut a little bit off this to make it manageable. Here's what we're going to do. Let me go to speaker view here. Lock on me. I think here's, oh, there is a bit of glare on that board. Here's the plan. Let's cut off part D, and part E is going to be special. Instead of doing part E as a homework problem, basically I'm going to make part E our lab. And today's lab is going to be kind of like math exercise training. I'm going to use the extra time to go around and make sure that everyone can handle these somewhat more complex calculations for Newton's laws. How many of you have a Casio today? Oh, I like your cat, Will. I forgot his name. What's the name of the cat again? All right, Joel. Joel, you're with me. What's your cat?
Amazon messed up my order.
Wait, what's that, Will?
It's Wolfgang.
Wolfgang. Yeah, Wolfgang. I like that dude. Okay. Great cat name.
Brendan.
Yeah.
I'm trying to figure out where the rest of the calculator is. This thing's so small.
Think of that as that's your sidearm, soldier. Just right there in your holster. You can quick draw, pull it out. You don't need too much there.
Yeah, but I like this rifle.
Well, so, you know, it's a tool for every job. So, well, I'll tell you what, Joel, keep them both handy, and you can try your calculations on mine, and you can try them on yours. And I'm betting you're going to end up like mine, but I'm not sure. Some people still stick to their guns, so to speak. The first problem doesn't involve too much math that we need a calculator for, but the next few will. So, Laura, are you kind enough to read us? We're doing chapter 4, number 45, and this is on the law of gravitation. We did cover this.
Yep. Okay, so part A says, how does quadrupling the distance between two objects affect the gravitational force between them?
Okay, so we're taking the distance, and quadrupling, of course, means 4 times greater. our job is to understand, okay, you know what? The natural light isn't working. I'm realizing now that there's quite a bit of glare on my board, so let me manage that. Hold on. All right. Let's start by writing down Newton's law of gravity, but let's not write it down the way I did yesterday with the constant big G in it. Let's write it Newton's style. Newton's version from his Principia Mathematica, oops, spelling, stated that the force of gravity was proportional to the product of the two masses and inversely proportional to the distance between them squared. For many of you, this is the first time that you've ever tried to work with a proportionality argument. This is a magical operator. It's not like equals. It has its own rules associated with it. But if you know how to wield this operator, you can make mincemeat of math problems in short order. The way this works is big G is not included because big G is a constant of nature. That's why they call it the universal constant of gravity. And its value for big G is 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Obviously, that's a bit of a mouthful. People get tired of saying 7 times 10 to the minus 11 meters cubed per kilogram per second squared. So they replace it with big G because it's easier to write. However, big G never changes. It's always the same. And in that sense, big G is kind of boring. What's interesting, or not uninteresting as my old professors used to say, is that the masses may change and the distances change. And the proportionality tries to explain what the effect will have on the force if you change one of these quantities. The way it works is you rewrite this each time only including the variables that you're going to change, but you have to leave the variables in their positions, top or bottom, and if they have any squares or cubes attached, you have to leave those there as well. Let's start with the distance and I'll show you how it's done. And then you'll follow after me. The distance is the only quantity that's being varied in this case. So for instance, you might imagine that we had calculated in our end of lecture last time the force of gravity between Earth and the moon. And we found it to be 2 times 10 to the 20 newtons. Okay, cool. What would happen if the moon had suddenly moved to twice its distance? How would that change the force of gravity? We're not interested in calculating the magnitude of the force. I don't want to know how many newtons per se it is. I do want to know how the force would vary. Would the force go up or down? By how many times? 2 times, 3 times, 4 times. Since I'm only varying the distance, I can rewrite my formula in the following way. The force is proportional to 1 over d squared. Notice the d stays at the bottom. The masses are no longer showing because they're not changing in the equation. For the second move, I substitute in the factor by which the distance will vary, as long as I use the proportionality symbol. The distance is varying by a factor of 4, so I have 1 over 4 squared. At this point, I have to transition from proportionality to equal sign, because now I actually have a quotient to evaluate. 1 over 4 squared is what, class?
16.
Not 16 over 1.
1 over 16.
That's right. You have to say that, because if you say 16, I'm going to think it's on the top. And the interpretation of that is the new force is 1/16 the old force. Or to put it simply, 16 times weaker. Okay, I'm going to erase that. Now it's your turn. Laura, what's part B say? Or anyone.
Sorry, I was muted.
Oh, that's all right.
Suppose the sun were somehow replaced by a star with twice as much mass. What would happen to the gravitational force between Earth and the sun?
Okay, Evelyn, let's start with you if I can. How would I write my proportionality argument in this case?
F is proportionate to M, like M1 times 2.
Well, are we varying both masses or just one of the masses?
Just one. Wait. I'm not sure.
Okay. Well, the way I remember the phraseology from the question said, what would happen if we replaced the sun with twice as much mass, right?
Yeah.
So in other words, I don't even know which planet they were comparing it to. They were vague about that. But maybe they were comparing the sun versus Earth, right? If I put this one in the foreground, it looks bigger. Okay, so we're increasing the mass of the sun, but the mass of the Earth, presumably the mass of the sun would be M1, and the mass of the Earth would be M2. But it doesn't sound like we're changing the mass of the planet. We're just changing the mass of the star. So, Evelyn, you could write force is proportional to M1 times M2, but the M2 isn't really changing here. You see what I'm saying?
Yeah, but M1 times 2, right?
Not times 2. We just write force is proportional to one of the masses. Only M1 changes, so we basically are rewriting the equation with everything else missing except for what is varying. Put it this way, do you know what the answer is?
No.
Oh, okay. All right, well then, this is useful. Wait, so let me make sure you understand that, Evelyn, because people often get confused here. I only included one of the masses. Tell me why.
Because that's the only thing that's changing.
That's right. That's what I wanted to hear. Now, in the next step, we substitute in a factor of 2 for the mass that is changing. So I'm going to replace M1 with a 2. And then this problem's kind of boring. I'm done.
So you just replace it, you don't do anything to it? You don't like...
Yeah, and the reason why okay, I can explain this to you in more detail, but I don't know if you're going to like it. The new force, hold on, let's finish this, is 2 times stronger than the old force. When you use a proportionality, you don't have to plug in the actual value of M, because proportionality means it varies as. You only have to plug in the factor by which it changes.
Okay.
A more elaborate version, Evelyn, would look like this. I have the old force, and the old force is G times M1 times M2 over D squared. I have a new force. The new force is G times the new M, M prime, M2 over D squared. Now I take the ratio of the two. When I take the ratio of the two, I find that the old force as a ratio of the new force, everything cancels out except for M1 over M1 prime. So I can basically just substitute in the ratio by which the masses change if I want to know the ratio by which the forces change. But that's kind of like a lot of fucking words, right? And a lot of symbols, and people don't want to hear that stuff. So instead, I'm just going to tell you something easy, which is the kind of upshot of it all. If you're only going to vary the mass, only leave the mass behind and substitute in the factor by which it changes.
Okay.
But there's logic to it. Okay. So, Evelyn, since I'm kind of torturing you right now. I will continue to torture you. What does part C ask of us?
Have to open it. Part C says, suppose Earth were moved to 1/3 of its current distance from the sun. What would happen to the gravitational force between Earth and the sun?
The distance is varying by a factor of 1/3. Now, I could call in someone else, but because I want to see if you've comprehended me, let's have you try part C again.
So you do F is proportionate to D squared, which is proportionate to...
Hold on. That is not true. You have just made a tactical error, and it's an instructional one. It is not true that the force is directly proportional to the square of the distance. That is false. Do you know how to modify it?
Be 1 over D2?
That's what I want to hear. And that's why we say the force is inversely proportional to the square of the distance. Inverse means D goes on the bottom, square means it's squared. So let's write that proper now. And now keep going with what you were planning on doing.
F is proportionate to 1 over D squared, which is proportionate to 1 over 1/3 squared.
Very good. Now be careful here. It's very easy to F this up. Watch how I do it and do it just like I do. I'm going to put the 1/3 in parentheses and I'm going to square it. Oh, what's that turn into? Now we can replace it with an equals, Evelyn, because we're evaluating a quotient.
1 over 1/9.
1 over 1/9. And what is 1 over 1/9?
9.
That's right. So what's the final answer?
The new force is 9 times the old force.
That's very good. The new force is 9 times stronger than the old force. Proportionality arguments probably seem pretty weird to some of you guys, but I want to tell you that scientists, professional scientists, use them all the time in their thinking, and they can be extremely powerful. You can sometimes arrive at answers much faster than some schlub who tries to plug all the numbers in, okay? So you got to trust me that they are powerful, and you need to learn them. This is as good a place as any. Okay, 45, down the hatch. Platoon. The next question is about tides. And I am debating whether I want to try to answer it now or whether I want to try to answer it in the class after I've introduced tides. In our lecture last time, we had ended calculating the force of gravity. And the usual chain of logic goes, I teach you a bit about the force of gravity, and then I teach you about tides. Why don't we do this? Why don't we hold off on tides? Can we hold off on the second question until lecture, and then we'll just, I guess it really doesn't matter if we do it now or we do it an hour from now, correct? Yeah. Let's move right on to the math ones, and let's get our hands dirty. So everyone remind me that we still have to do 47. We're going to jump to 56. Okay? Everyone comfortable with that? All right. Laura, can you read us number 56?
Yep, let me just get back to it. Understanding Newton's version of Kepler's third law. Find the orbital period for the planet in each case. Hint, the calculations for this problem are so simple that you will not need a calculator.
That's a lie.
So A says a planet with twice Earth's mass orbiting at a distance of 1 AU from a star with the same mass as the sun.
Okay. Now, you guys only learned Kepler's third law in your previous lecture, and now I'm going to be giving you a new version of it. So before we get into the problem, as part of our homework and also as part of our notes somewhere in between, let's do a contrast between Kepler's third law and what's going to be called Newton's version of Kepler's third law.
This is number 56, Brendan.
Yes. Oh, yeah. Thanks, Joel. Holy crap.
Just so people don't get confused if they watch it
No,
later.
hell yes. That's very right. You are right to point that out. I'm sorry.
It's all right.
I'm even confusing myself here. Okay. Guys, why don't you do me a reminder on Kepler's third? You can look at your notes and cheat if you want to.
P squared equals A cubed. It's the
Good. Now,
harmonic.
the big thing about p squared equals a cubed, it has very particular units in order for it to work. And was that Evelyn that was talking to me, or was that someone else?
That was me, yeah.
Evelyn, can you remind us of the units of p squared equals a cubed?
The P equals period of planet in years, and the A is the average distance between the planet and the sun in AU.
Okay. I'm here to tell you some important rules about Kepler's third law. And let's take them as sort of notes right in our homework. Kepler's third law only works hold on, it doesn't have to be a planet. It only works for orbits around the sun. This is an important point. So in other words, it will work for planets. It will work for comets or asteroids. They orbit the sun. It will not work on moons. It will not work on satellites. It will not work on the sun going around the center of the galaxy. It basically works for planets, comets, and asteroids. That's it. Okay? In that sense, Kepler's third law is a limited orbital law. Isaac Newton discovered the real version, the scary version, which you can use in any situation for any two orbiting bodies. Oh, by the way, because it'll be important context in our class, also put an X next to binary stars, because you're going to learn the shit out of some binary stars this semester. It will not work for binary stars. So that's an important context for this class. Okay. How does Newton's version look? It's got a p squared and it's got an a cubed, but it unfortunately has some other junk in its proverbial trunk. P squared equals 4 times pi squared times a cubed divided by big G divided by the addition or the sum of the two masses. Now that formula looks kind of scary first time you see it, but you will quickly become friends with it, and it'll be like an old glove that slips right over your hand. Oh, unit issues while we're at it. In shocking red. From now on, the period will be measured in units of seconds. The A will be measured in units of meters, and the masses will be measured in units of kilograms. In other words, this is an MKS kind of formula. And most importantly, one single sentence. This works for any two orbiting masses M1, comma, M2. So with that in mind, that was almost like notes, because it's sort of the background you need to do the job here. Laura, could you read that out again while we look at these two formulas?
So it says a planet with twice Earth's mass orbiting at a distance of 1 AU from a star with the same mass as the sun.
Okay. So it's going to turn out that because the star has the same mass as the sun, we actually could probably use Kepler's third law. But that's not the point. The point is you're supposed to try Newton's version of Kepler's third law. That's why the title of the problem is Newton's version of Kepler's third law. So I am going to force us to do it this way, all right? So I'm going to erase. Everyone cool? Everyone caught up here? Here I go. Okay, I want you to write it up the way I do. M1 will be the mass of the sun. There's a symbol that I like to use for the mass of the sun that I would like to introduce now. It's an M with a circle and a dot. That is the old astrological symbol for the sun. It's cuter than writing M sun. M2 is going to be twice the mass of Earth. There is a symbol that we use for the mass of Earth. It's a mass, a circle with a cross in it. Circle dot is sun, circle cross is Earth. You're going to see me use those symbols a whole bunch. So I'm just kind of getting you used to them now. I happen to know the mass of the sun. The mass of the sun is 2 times 10 to the 30 kilograms. I happen to know the mass of Earth. The mass of Earth is 6 times 10 to the 24 kilograms. I'm guessing y'all probably know the distance between Earth and the sun, right?
1 AU.
And Joel, how many kilometers is that?
150 times 10 to the 6 kilometers.
How many meters is that?
150 times 10 to the 9th meters.
Hey, this man's got some chops. Just in case you aren't as good as Joel, let's put kilometers on top. Oh, sorry. Let's put kilometers on bottom. Let's put meters on top. There are 1,000 meters in 1 kilometer, and Joel has trickily added the 3 zeros to the 6 to get 150 billion meters. We're doing that on the express docket because he was good enough to do it for us. Okay, now it's time to punch all this crapola. Notice we had to get our distance into meters. That's going to be important for you guys. I'm going to write all of this out. Now, first I want you to watch me write it symbolically, and then we will substitute in values. Now, what I like to do is I like to solve for the period right away, and I like to put the square root on the other. I like to take the square that was attached to the p and flop it over to the other side and make it a square root. So this is how it's going to look. It's going to look like p is equal to, make sure you make a nice big neat square root so I can read this carefully, 4 times pi squared times a cubed divided by big G times the mass of the sun plus 2 times the mass of Earth. And we're going to rewrite this in a second, substituting in all our values. But I think it's kind of good for you guys to see the Trying to block the sun. Okay, I'm doing a shit job. I think it's good for you guys to see the whole thing written out. Okay? Rather than right below it, I'm gonna erase and do it again. So I'm gonna write it again, this time subbing in some values. Watch how I do this. I put parentheses. I think I'll put my units in red. 150 times 10 to the 9 meters. And then close parentheses and I cube it. Students, the reason I put the parentheses around are not for your calculator, but because the cube root must be distributed not only to the number, but also to the units so that our units balance out. Now we'll put in big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Now I'll put in, okay. Let's pause here for a second. Sometimes, occasionally, we can replace the sum of the masses with something called M total, the total mass. Let's take a sidebar here and calculate the total mass for simplicity. It's the mass of the sun plus twice the mass of Earth. And that is 2 times 10 to the 30 kilograms plus 2 times 6 times 10 to the 24 kilograms. I'd like you guys to start with just that calculation there at the bottom. So take your calculators out. We're going to do this part first. We're just going to do 2 exp30 plus 2 times 6 exp24. Sarah, what did you get? Sarah, I don't suppose you got your Casio, do you?
No, I'm still writing down too.
All right, well, keep writing. Going a little too fast for you guys. Can't keep up with an old man here. Sarah, do you ever plan on getting the Casio?
Yeah, I ordered it too. I'm just
Oh,
off of Amazon. I'm waiting for it.
that's right. I think we had this talk on Tuesday. I forgot. Sorry. Well, as long as it's coming. In the meanwhile, you've got your phone thing, right? Is that what you were using?
Yeah, I'm using my TI-84 now.
Oh,
Seems to work better.
that's cool. You know, use the double E key instead of the EXP, right?
Yeah, I usually just use the caret, but
No. Please don't do that. Sarah,
it depends on.
could you do me a favor since you're using the TI-84 today? And we're going to do a lot of calculations today. You want to get them right. Would you please just use the double E key every time? Just do it as a personal favor. Sarah, the reason has to do with order of operations. When we get into some long calculations like this, we want to make sure that the lead digits are glued to the power so that we don't have any order of operations issues.
Okay.
I know there are reasons for this. Anyway, Sarah, why don't you add them up and tell me what you get using your double E key, of course. And you know where the double E is, right?
Yeah.
It's just above the 7 on my TI-85, so it might be around there for yours too. Zoom tight. What'd you get?
I'm not done yet. You know what? Can someone else do this one? I think.
Wait, no, Sarah, this is important. If it's causing you troubles, then that's all the more reason to do it. I know what I'm talking about. We can just take some time and we can get this right. I built the time in for us to do this. So watch me and punch after me. Unfortunately, I've got to replace the batteries in this thing, but look, just, can you see my calculator? I'm asking you to do this. 2 double E 30 plus 2 times 6 double E 24. That's what I want you to do. And whatever you get, just tell me what it is. Is your double E key in the same
Right
place?
behind you.
Oh, sorry. Sarah, I want everyone to do this. And I'm going to give everyone else the same torture that you get. Don't you worry. And if you're getting confused, you got to talk to me about where you're getting messed up. Do you see something or?
I mean, yeah, I don't know how to read that to you.
Okay, well, that's part of your training and learning. This is what it looks like on my calculator. Is that what it looks like on yours?
Yeah.
Okay, well then at least you got it right. So remember, you got a lead digit, you got some change, and you got some power. You have to insert the times 10 yourself. So
Okay, so would it just be 2 times 10 to the 30th?
pretty much, yeah. That's what I wanted you to say. What are the units?
Sure. Oh god.
Well, what are the units going into?
Kilograms.
That's right. But Sarah, I've got kind of a beef about that. Okay, now that we've gotten that part out of the way, I'm kind of confused. Isn't 2 times 30, 10 to the 30 kilograms? Isn't that just the mass of the sun?
Yeah.
But I thought we were adding the mass of Earth to it. What happened?
Don't know.
Does anyone know? Why did I get back the mass of the sun?
Because the Earth is
Jose?
so much smaller than the sun.
Oh, wait, hold on. Joel just said something smart. What was that?
The Earth is so much smaller than the sun.
It doesn't fucking matter, right? Even a planet twice Earth's mass does not significantly add. Now, this is an important trick, and you got to know when to play the trick. In fact, Sarah, I really just made you do that for nothing. I want you to know that, okay? You did that for absolutely no reason whatsoever. The mass of Earth is tiny in comparison, and it can be ignored. So sometimes we can just replace the total mass, this is a trick, with just the mass of the sun. And that's what we're going to do. We're going to substitute that in, all right? Let's plug in the mass of the sun. 2 times 10 to the 30 kilograms. Now, Sarah, if you liked that last one, oh, God damn it, are you going to like this next one, okay? You're going to really enjoy this because you've got a big whopper to plug in for me. In fact, because we are all using different calculators, this is going to suck extra hard. I'm going to explain how to do this for the Casio people first. Then I'm going to explain it for the people who have line entry calculators like Sarah. The people who have line entry calculators have calculators so you can plug it all in one shot. And there are different logics that apply. Let's start with Casio people first because they're my favorite. When you plug this in, Let's strategize together. You're going to do it in the following way. I want you to listen. Listen to me carefully. You will multiply 4 times pi squared times, there will be no parentheses at all because we're using our exp key, 150 exp9, then we're going to hit shift cube. Here's the important part. We will divide by 7 exp minus 11, and then here we will divide by 2 exp30. In other words, even though it says times there, you will not hit times, you will hit divide. Then you will hit equals, and after that, we're going to square root. Okay, now it's time to talk to line entry calculator people like Sarah, and I noticed a couple of others of you were using calculators where you punch it all in at once. In those calculators, we should probably plug the square root in first and open parentheses. In fact, I should try to swap out my batteries so I can show you how to do this. Why don't you guys with the Casios get going and punch it in? Wow. I guess this is what the inside of your Casio looks like when you haven't used it since 1996. Not good. Who is better? You just come and lay down here? Huh? Yeah, triple A's. I need 4. All right, thank you. I don't have triple A's anymore, guys. All right, Sarah, you're gonna have to work with me here, okay? Do you know where your square root key is, Sarah? Sarah, talk to me.
Sorry. Yeah, I do.
Okay, so hit square root, and then I want you to hit open parentheses, okay? Do everything I say, do it just like I say. Square root, open parentheses, 4 times. Your pi key, where the hell was the pi key on this? Mine is above the caret. Is that where yours is?
Yep.
So shift pi, and then we have an x squared key next to the 7 squared times 150 double E 9 caret cube divide by 7 double E negative 11 divide by 2 double E 30 close parentheses equals. Tell me what you got. In fact, Sarah, I'm going to be asking you all the time. Show me what you've got in your calculator. Put your calculator up to the screen so I can see what you have.
I'm still on the top.
All right. You didn't pay me
I thought that the
$500.
parentheses like off.
Can you show me? Just show me. Put your calculator up to the camera. I want to see what's going on there.
It's right after the 3. I'm just trying to fix that.
Oh, yeah, delete that, and it has to be on the.
I know I can't.
Get rid of that altogether, and just hit divide by there. What you do, I know how to fix that too. See, this is why we all need the cassette. You have to hit the arrow key. Look at me. Hit the arrow key to get off.
Yeah, I am. It's just going over it. It doesn't.
All right. Keep going. Keep going. You can do this.
I can't because
I-
it divides the fraction or the.
Can you show me? Can you show me? Wait, hold on. Let me full screen you. All right, don't get frustrated. Just show me. We'll work through this. Can I see your calc? I usually know what to do. It's, oh boy, here we go. Try going back 2 spaces and hitting delete twice. What happens if you do that?
I know it's just gonna clear all of it.
Wait,
Isn't it?
delete clears all of it? Don't hit clear. Isn't there a delete? Look, on my calculator, I got a delete key here. See? I got a delete. Unfortunately, I don't have batteries for this dumb thing. Otherwise, I would do it with you.
Sarah, if you're over that last parenthesis and you hit clear, it should clear that without clearing the whole thing.
Oh,
I
clear?
think,
It usually
if
doesn't
I
let me-
remember right. I have that same issue of mine. I think that's how you do it.
Okay. We'll listen to the wisdom of Joel then. Remember, Sarah, to divide by 7 exp minus 11 and divide by 2 exp 30, close parentheses equals. Okay, how about the rest? Let's talk to someone else. Hey, Catherine. What's kicking, chicken?
So
What do you got?
I don't have my calculator yet because
Oh.
Amazon lost my package.
Guys,
Oh, no.
So I have somebody literally going out to get me one, and it should be here by lab.
all right.
Because Amazon, I've been fighting with Amazon for like 3 days, and they've lost many packages of mine, not just the calculator, so I'm not happy.
Normally, I would
That's
say just go
sad.
out to Staples, but I can understand in these COVID times wanting to get everything contactless.
I've been trying to, but it's like I work to a point where it's like I can't run into the store afterwards because everything's closed.
Yep,
So
I know.
I have somebody running out.
Okay, all right. Well,
I'm
noble effort.
sorry.
That's okay. In the meantime, because you need to be learning every moment, could
Yeah.
you try plugging this into a crappy phone? Yeah, but you need the scientific version, so you have to go sideways, I think, right? If you rotate sideways, it should give you all the buttons. So just mash it.
So
This is,
when
yep.
when I try typing it in, like, because I was trying to do it with you when you were doing it on your calculator, I couldn't find the square root.
Can I look at
symbol
your
on
screen?
mine.
I'd have to see. Oh,
Sideways, it's like the third row down and 1 in. It's like the little 2 over the X, or like the 2 square root X.
Okay,
is that it?
I found that.
I can also, oh, good. Okay, thank you. I'd also, remember, you're going to do the square root at the end, though, because you don't have a line entry calculator. You have like an instantaneous calculator. And in fact,
Okay.
I'd recommend that you try to get pan ecal.
I have that.
Why don't you try using that one? That one's going to be a little more elegant.
Okay. So will I do the square root first or after at the end?
You're going to do it at the end after you hit equals.
Okay.
I just had my phone and I put the fucker down here, and now I want to follow along with you so I can see what you're doing. Oh.
Yeah, I'm doing the same thing as you, Catherine. I'm on the iPhone. Hey, Evelyn, I didn't realize that one was the square root. What's the deal with that one with the 1, 2 from it that has a
No.
Y and an X?
Guys, how about fuck that noise? Could we just download pan ecal? Because this is already getting horrible. This is what I was trying to avoid. And now you can see, when I tell you to do something, there's usually a damn good reason for it, okay? It's because this ain't my first rodeo. This calculator will be much better to do it. I want you people using phone calculators to watch how I do it on pan ecal. First, I clear. What the hell? Get rid of this. Okay, you clear it out. And then I would do this. I would do 4 times, where's the bloody pi? Pi, and then I would hit square, okay? Actually, this is line entry style. So now that I think about it, I'm going to square root this. This is the same way Sarah should be doing it, okay? Square root of 4 pi squared, let's go over here, times 150 exp 9, okay? Come on, focus, 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 focus. Fucking stupid webcam. Okay, and now I'm going to hit my cube key to the power of,
You don't
I can't
listen.
do it backwards. Delete. To the power of 3. Oh, this is evil. Divide by 7 EXP. What a backwards ass calculator. Do you use the minus key for negative? Where's the negative on this?
Yeah. Should I
Negative
tap my card with this?
11
All right.
divide by 2 EXP30. Unfortunately, that's what it had to look like on Panny Cal. I think you used the minus key for negative.
And then, yeah.
I have the Panny Cal. I swear to God, it is easier on like the iPhone when you tilt it sideways for me. But you're right. I mean, we
No.
just gotta get-
If it's easier for you, give me the fucking answer. How about that? What's the answer? Okay. How about we try that? I know anyone except for Laura and Shay, because Laura and Shay already have training. So you guys are boring to me. I want to hear about the rest. I'm more interested in mucking around with. Sarah's gone. She's hid her video for me, so I can't call on her. She's gone dark.
Sarah
Okay.
hates your guts now. You're screwed.
Will, what you got?
1.5 times 10 to the negative 15.
Nope, that's wrong.
Ah,
Joel, what'd you get?
17.4 times 10 to the 6.
Wrong. Well, wrong. 17.
Well, you
Wait,
you want the whole number?
no. Hold on. You threw me off guard. 17 times. I think that's right, actually. 17 times 10 to
I
the
typed
6.
in my Casio the way you told me.
You did it right, son. You got it right. So 17.4 times.
Damn it! I followed instruction and you still told me I'm wrong.
Okay, I'm just used to people being wrong. Okay, being right is the
quit.
okay,
We're all
hold on.
quitting now.
You did it right. Hold on here. So Joel got 17.4 times 10 to the 6. What are your units?
Let me read the question again.
No, it's not about that, Joel. It's about doing unit analysis here. What units can you cancel out?
Kilograms,
That's right. What else can you cancel out?
meter squared.
That's not a meter squared, buddy. That's a cube.
Or cubed, yeah. The M's.
What do you have left over?
Second squared.
You have the square root of 1 over second squared, which is the square root of second squared, which is what?
Seconds.
That's right. It's a period. It's a unit of time. I want to see it in all your calculators. Show me. Catherine, show it to me. Sarah, come back. Don't hide from me.
Messed up.
I want to torture you some more. I can't torture you if you're hiding. Show me, Catherine, show me what you got.
Well, I just cleared it because I was way off.
Well, punch again then. Do you want to grow old and die together? I mean,
Hold on.
this is going to be an important hurdle in our class, and I want to get over it right. Now, I could let people just slink off into the shadows and not show me anything, and then that's going to lead to some very dark and evil times in the future. I'm not letting that happen. No soldier left behind. Evelyn.
I have a problem putting it into, because I'm using this like phone calculator, which has been fine until now.
Exactly. Fine until now. I knew this.
My graphing calculator, that I can't find the charger.
Shit. All right. Could you download Panny Cal then?
I just did. It's more confusing than this one, but I have it keeps saying an error. The only problem with the input for this one, it keeps saying an error when I try to do the 150 times 10 to the 9th to the 3rd.
So here's the deal, Evelyn. With that calculator that you're using, the moment you plug it in, stuff disappears. So I can't diagnose it. At least with Panny Cal, I can see the whole thing written out, and I can say, there's where you went wrong. Do you see what I'm saying about your calculator? I think it's kind of instantaneous. There's no history. All right, just show me the, I don't, what calculator are you using? Let me get the calculator you're using. Where is it? What is it?
It's just the regular iPhone calculator.
I think I threw that one away. Hold on.
I can
Oh.
use.
I don't know where that app is on my app anymore because I think I hated it and I destroyed it. Can you destroy it?
I don't know. It's an iPhone app. I don't think they let you.
But the problem is I don't
Nazis about
see
that.
it. I've never used it. I decided I hated that one the day I saw it, and I hid it from myself. So I can't diagnose your problem because I don't have that calculator. I do have Pan Ecal.
Yeah,
And
I'll just use that one. I have that one too.
oh, Joel, you're a little bit wrong. Joel, you're wrong. You're wrong. I take it back. You are wrong. This is the right answer. I'm not even telling you the right answer. You guys have to get it. Okay, Sarah, what's happening on your calculator? I want to go back to Sarah. I'm never going to get tired of talking to Sarah. Sarah, what's happening on your calculator? Did you get a number for me? You're muted, buddy.
I just switched to the Penny Calc.
Okay. Hey, Jose, I haven't talked to you yet. What's happening with you?
Okay, I want to take a really wild guess here.
Yep.
You said you're not going to show the answer, but okay, I cleared my whole thing because you said Joel was correct, and I think I typed it in wrong, but
Maybe you typed it in right?
Yeah.
I forgot what the right answer was for a second, Jose. I know I'm not helping things with my inconstancy. I'm fickle. I'm a fickle instructor.
I only remember it starts with 17 point.
No.
Damn it.
Okay, which calc are you using, Jose? Are you using the Casio?
Casio, yeah.
All right, you're the man I want to talk to. All right, you punch with me, okay? You do everything that I do. Watch my moves.
Yep.
Okay, see my calc here?
Mm-hmm.
4 times pi.
Yep.
Square key.
Mm-hmm.
Times 150 exp9 shift, this is your cube. Ooh.
Mm-hmm.
Divide by 7 exp negative 11.
Mm-hmm.
Divide by 2 exp30. That's what's up. Now
2 exp30.
Now wait, hit equals first.
Okay.
Now shift square root that. That's your man. See, he's using a calculator I like, and I like him. So what you get now, can you put that in the scientific notation for me? Because it's way bigger than a million. 3 sig figs.
So 309.
The number after 8 is a 4, so you do not round up.
Okay.
Don't say 309, say 3.08.
Okay, 3.08 times 10 to the 6.
Count better. Count better.
Then 9.
Count even better than that. All right, we got to do this together. Jesus, hold on.
How many days are in a week,
Meridian
Jose?
pencil out. Watch. Joel? I'm sorry, not Joel. Jose? Jose.
Yeah.
We start. Do you see my calculator here?
Mm-hmm.
Come on, focus. We start with the decimal point there. We go 1, 2, 3, 4, 5, 6, and
7. Okay.
That's what I want to hear.
I started counting it from the 4, so I started counting it from the wrong side of the point. So
don't do that anymore. Count from the decimal point to where you moved it. Okay, listen. During a normal lecture, I go around to every desk and I get in your face and I make sure everyone has the right answer. This is obviously harder for 2 reasons. 1, I can't physically get in your face. 2, I can't see. You're all using crazy calculators, which is what exactly I was hoping to avoid. But here we are, so we're doing it, and life sucks. So let's go one by one. Catherine, what do you got? Show me.
Oh, well, hold on. When I did it time, I messed up again. So I was
And
waiting.
I need you to punch it again.
Okay.
I don't want to
hold
hear
on.
any excuses. I want you to punch. Evelyn, what do you got? Punch and show me something.
I'm punching it into any cal. I couldn't
Punch it.
find
Joel, what do you got? Did you fix your problem?
Yeah, I don't know what I did.
Do you have the right answer now?
Yeah, I got 3.08.
Laura, you got the right answer, right? Awesome. Shay? Shay?
Yeah,
What do you got? Pens between your teeth. You look like you're in the middle of the, you're in the shit
I was.
there.
I actually, I have ERROR.
Okay. What calculator are you using? PannyCal?
No, I'm using
Nope. Switch to PannyCal. Obviously, that's not working for you. So that guy's done. Go to PannyCal. Can you do that for me?
absolutely.
If you're not using the Casio and you don't know what you're doing, use PannyCal. Sarah, you can continue on with that thing, but we got to, hold on. Jose, you got the right answer now. Will, talk to me. What do you got? No. That's not how this works. Unmute you. I can unmute you. Can I? No, I can't. You're muted. Yeah?
Yeah, I'm trying to plug it in.
What are you using?
I'm using the solar, the 260
Oh, fuck yeah. All right.
Casio.
I can work with that. Come here. You do exactly what I do. Everything that I do. Okay? Where's your face?
I'm right here. I'm right here.
The Casio's there for, oh, there you are. Okay. Watch. You looking at my calculator? You punch
Yeah.
a P right now. 4.
Yeah.
Ready? 4
Yeah.
times. Hit
Yeah.
the EXP for pi.
Mm-hmm.
Now the square key.
Mm-hmm.
Times
Mm-hmm.
150
Mm-hmm.
EXP 9. You with me?
Yeah.
Shift cube root right there. Little arrow key.
Mm-hmm. Yep.
Divide by
Yep.
7. EXP
Mm-hmm.
11. Negative.
Oh, that's what I was doing wrong.
No, that's
oh, wait,
okay.
Never mind.
You
Keep
could
going. Keep going.
You
I
could
did
do
it the other way.
Negative
Yeah.
first. It doesn't matter.
Okay.
Divide by. That's what you were
Yeah.
doing wrong. Divide by 2 EXP 30
Mm-hmm.
equals.
Mm-hmm.
Is that what you see?
Yes.
Now
Yes.
shift square
Yeah.
root.
Oh, that's what I was doing wrong. Okay, I have it now. That's the thing I was doing wrong at the end.
Good.
The
Well,
square
whatever
root
you were doing
thing.
before,
Okay.
don't do that no more. Okay?
All right, got
Only
it.
do the right thing.
Okay.
Okay. Sarah. Sarah, can you hold your calculator up so I can see what you got? I want to see what you're punching in, and then I can work with you. So I've actually made you large.
You need a square root at the end?
Well, you're going to be doing the square root first. Can I just look at your entry so I can diagnose what's going on? I just want you to hold your calculator up to your camera for me.
Well, I think I can get it now. I just messed up just now.
That's okay, but the square root, you have different instructions. So here's what you're going to do. Just hold your calculator up to
Well,
the
I
screen.
switched to PannyCal.
Oh, okay. PannyCal. So then you and I will do this together, okay? So I'm going to clear it out. We're going to punch it in together. Let's watch me. Let me get myself on the screen here. Hold on. We cannot move forward until every single person can do this. Cameron and Alba, I'm going to figure out how to torture you in a second. Okay. Do you see my screen, Sarah?
Yep.
Punch with me. We're going to do square root first. Bear with me. I'm going backwards here. 4 times pi. Oh, shit. I'm going to hit the caret now. Focus. Focus.
Back up.
Okay. I'm going to hit these keys are very small and I'm trying to do it backwards. And the moment I take my phone away, it loses the focus. And I can't use my phone. All right. Hold on. I got a better idea.
I have it
Where's
set
your
up.
phone?
I've got it correctly on my Panny Cal if you want me to hold it up to the screen.
Yeah, but it's important that we punch together. See, that's not gonna, Catherine, that's not gonna help. You've got to do the keys together. I got a better plan. Hold on.
Brendan, where's your phone holder? Your phone stand?
It won't help because I'm using my phone. What I want to do is get my iPad and see if I can use my iPad with Zoom. Hold on.
Yeah, if you get your phone stand and then put your camera down to it, it should work.
Joel, I got an even better idea. God, this sucks. Okay, hold on. Share screen, iPhone, iPad, share. Okay, I'm now sharing my iPad with you. And I think there's a camera app on here somewhere. There
Photo, video,
we go.
middle of the left-hand
All right,
side.
Sarah, are you watching me?
Yep.
Okay. This is what it's come to right here. Okay, let me find your face, Sarah, so that I can interface with you while I do this.
I'm doing it with you too. It's Shay. I'm doing it with you too.
All right, okay. So multiple peeps are doing, is someone calling me? Get out of here. Get out of here. Okay. All right, do you see that? Look at that. It's larger than life. Do you see that?
Yep.
Okay. Now I can see what I'm doing at the same time. You're going to hit this button, x to the power of y, to raise to the power of 3. Then you're going to close parentheses.
That should be power to 2.
Oh, she's right. I suck. Hold on. Doop, boop. Thank you. I'm going to hit the power of 2 key then. What the hell's wrong with me? All right, did you backspace and do that?
Yeah.
All right. Times. We're going to do this a different way. 1.
Don't you need to do close parentheses, Brendan?
I just
No,
hold on.
nope. No close parentheses. Just trust me. I know what I'm doing. EXP9.
Wait. I
Yep.
accidentally did it. Let me just get caught up. Hold on.
Let me know when you're up to where I am. I decided I don't like Panny Cal either. I only like the Casio.
What's up?
Okay, we're gonna hit to the power of x to the power of y. I wish those parentheses weren't there, but they are, so fuck it. 3. We're gonna do divided by 7 exp. I think you have to use the minus key, which is evil for 11. Divided by 2 exp 30. Fucking hate phones. Now we'll close parentheses. Do you have all that?
Yep.
Hit equals. Show me that number. Hold it up to the screen for me. I need to know you can do this or we're wasting our time. Okay, hold it up. Something went wrong. Wait,
Yeah.
Sarah. Wait, just keep holding, keep holding. There's a 2.19874. Can you delete all that? Can you just hit delete until you get back to the 30 and then you're supposed to close parentheses for me? You hit some wacky stuff.
I got that a long time ago on the iPhone calculator app, but I
Still getting that.
switched to.
Wait, Sarah, did you punch equals after the, did you do close parentheses equals? I did not see a close parentheses equals in yours.
Hold on.
Why is it flipping? Why am I seeing my
Oh,
ceiling?
that's what I got.
Wait, what? Oh, it's because my calculator, I was seeing the reflection of the ceiling in my calculator. Okay. Hey, can you show me your screen again then, Sarah? Oh, yeah. Booyah. Thank heavens to Betsy. Okay, who else? Who else isn't getting it? I'm done torturing Sarah now. Listen, I ain't going forward until I know you can all do it. Cameron, Alba, I don't know what the hell you're up to. You got it, okay? At least I've got 9 of you here. Or 1, 2, 3, 4, 5, 6, 7. I got 7 of you. I love it, Catherine. I love it. Yay. Okay. Cameron, you got it. All right, Cameron. Alba, talk to me, buddy. All right. I have the same one. Okay, good. Here we go. Hey, remember back in lecture 1 where I was like, it's a really good idea for us to all have the same calculator? There was a reason for that, right? So let's do it. Let's all get the Casio FX260 Solar. Okay, we're moving on. Now,
Hey, Brandon.
yeah.
Brand, I just have one question. What the hell? What's the caret? I have P-Calc. I just don't know what you keep calling the caret. I can't figure it out.
Oh, yeah, here. Let me show you. Hold on. Oh, you found it for $9, Cam? Was that Cameron? Who said that? Hold on. Shay, I'm coming
Alba
to
got
you.
it for $9.
$9? Can't
Yeah, it was
beat it.
$9.
Yeah, that rules. Hold on, I'm
It's the
coming to
key
you.
under
I'm just.
Brendan, it's the key under the alt, right? The
Yeah.
triangle.
You're talking pan-ecal, right?
Yep.
That's the caret right there.
Oh,
X to the power of y.
Oh, why do you call it a caret?
Because when you're typing code in, the raised to the power key is the caret key.
Oh, okay.
Here it's x to the power of y. Every calculator has their own language, which is why it's terrible for all of us to be using different ones.
Okay, gotcha. That was the only question. Yeah, I'm all set.
And I
Thank
was
you.
doing it without even realizing I was doing it, you know? All right. Communication is hard, guys. Communication is hard. Don't get frustrated. Just do what I tell you to do. Okay. That was part A. Oh, this is going to be a great day. All right, that was part A. How are we doing on time? Probably not very good.
11:30.
Fuck. All right,
Yeah.
we gotta move here. Let's do part B pretty quick. What's part B say, Laura?
This is number 56, right?
56?
Part B is, yep, a planet with Earth's mass orbiting at a distance of 1 AU.
I'm sorry, we're not done yet. We're not done yet. Unfortunately, for you to get the instruction on this problem, you got a period in part A of 30 point, was it 8?
30.08.
Times 10 to the 7 seconds.
Oh, 3.08. I need us to convert this to years using dimensional analysis. That's important. We're going to use a conversion factor that I'm going to give you in the interest of time. 1 year is 3.15 times 10 to the 7 seconds. Put that down in your notes. That's a key conversion factor from years to seconds. Jose, you're my resident dimensional analysis expert. Can you please help me convert 3.08 times 10 to the 7 seconds into years? You'll use the 4 steps of dimensional analysis. Look for the smiley face.
Write down the numbers to convert with its units.
All right, so what do I write down?
1 second. So writing down P.
Yep, tell me what to write.
3.8 3.08 times 10 to the 7th seconds
Step 2.
multiplied by division line.
Step 3.
Put units in first to cancel.
So
So we'll put seconds on the bottom. And you said we're converting this to years, right?
correct.
So years on the top.
All right. Step 4.
Put in the numbers in second using conversion factors.
Okay. So
1 is on the top,
yep.
and then 3.15 times 10 to the 7 seconds is on the bottom.
Okay, punch them up. 3.08 EXP7 divided by 3.15 EXP7. Punch them up.
3.08 or 30.08?
If you do,
3.08.
if it's 30.8, it's times 10 to the 6. I'll tell you why we're getting confused between those two, Evelyn. Evelyn, sometimes I like to put things in terms of millions. So sometimes in the past, I'll write this as 30.8 times 10 to the 6. You guys naturally put it in as 3.08 times 10 to the 7, so I left it there. It's the same number, right? Evelyn, can I try this a different
sorry,
way? Evelyn,
No, I just wrote down the wrong thing. Sorry.
this equals this.
Yep.
Okay. Jose, what do you got?
I haven't typed it in yet. I had to write other stuff down. Sorry.
Okay. Well, let's get moving here. Normally in class, I walk around to everyone's desk, and this is a lot easier. This is one of the challenges of being like not face-to-face. This is a moment where face-to-face would have really helped me. Also, you know what would have helped me? If you guys had all got the fucking calculator on the second day like I asked. That would have helped me too.
I don't remember you telling us to get that calculator.
Watch the goddamn video. I talked about it for like 10 minutes. You know, this is
I'm
great.
totally
He said, she said, no. I got
screwed.
recordings. I got recordings, okay?
Yeah, I don't recall that. No.
Don't make me call up my YouTube. All right, what did you get?
I got 3.17 times 10 to the negative 8.
No, poppycock. Come on. Look. 3.08 EXP7 divide by 3.15 EXP7. That's all I want you to do. That's what I get.
Oh, okay. I put freaking 1
Oh, don't do that.
divided by, okay. Sorry.
This divided by that. That's all we're doing here.
Mm-hmm.
And the answer you're supposed to get is approximately 1 year. And then we're supposed to say, duh. Of course the period will be 1 year. It will be 1 year because the mass of the planet is too small to influence the period of its orbit. That's the teaching message here. Yeah. Okay. Can we move on to part B?
Yep.
All right. Look, you guys are weak right now. You need to get stronger. You need to get faster. We will do that eventually. I'm going to erase. Laura, read me part B.
A planet with Earth's mass orbiting at a distance of 1 AU from a star with 4 times the sun's mass.
We've already learned that 1 AU is 150 billion meters. I'm not going to prosecute that again. The mass, I'm sorry, what was the mass of the star? 4 times the mass of the sun. The mass of the planet was the mass of Earth. The period is equal to the square root of 4 times pi squared times a cubed divided by big G times 4 times the mass of the sun plus the mass of Earth. Hey, Joel, what do you think about 4 times the mass of the sun plus the mass of Earth?
4 times the mass of the sun.
Exactly. As Joel points out, we can neglect the mass of the planet, as if twice the mass of Earth didn't count for the 1 star mass, then 1 planet mass is certainly not going to matter for the mass of the sun. So let's plug in our values now, right after me. P is equal to the nice big neat square root of 4 times pi squared times 150 times 10 to the 9 meters cubed divided by 7 times 10 to the minus 11 meters cubed per kilogram per second squared times 4 times 2 times 10 to the 30 kilograms. Okay, Sarah, get ready. Everyone punch. Everyone's got to punch. I am going to show you on the, here's what we're going to do. It seems we've broken into 2 camps. There's the Casio FX260 solar camp, and then there's the Pan eCal camp. I'm going to show you how to do it for both camps. Please watch me, and Wolfgang, you keep an eye on Will. Make sure he doesn't do anything crazy, okay? All right, so here we go. Watch me here. I'm going to start with the Casio people because they're my favorites. Hold on, wait. Do you guys need a moment to write this down? I bet you're still writing, aren't you? All right. Casio people, here we go. 4 times pi squared times 150 exp 9 oh shit, I forgot the cube. Let's try that again. Sorry. 4 times pi squared times 150 exp 9 shift cube divide by 7 exp minus 11 divide by 4 divide by 2 exp 30 equals shift square root. Okay, get ready, Pan eCal. Pan eCal, folks, coming up. Let me turn off my display brightness. Share screen. Phone. Nope. Hey, I just had you. Don't look for Apple TV. Look. No. No. I just saw Zoom be Britain, and then it looks for my neighbor's Apple TV. Maybe I should hit them with a little calculation. Okay. Nope. Ugh. So somebody's using an Apple TV nearby. Does anyone have an answer?
I got 15,424,913.
Like hell you did. Now that might be right, Evelyn, but that's way too many significant figures. Most of those numbers were garbage. How many significant figures do you get to keep?
2.
At best. I'll let you keep 3 for fun. But 2 is probably it. Actually, 2 is all you get, Evelyn. Forget about it, 2. So what's your answer to 2 sig figs?
It's, sorry, there's a huge wasp flying around my head and it's freaking me out.
Oh, okay, that's scary.
It's 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7.
Units?
Years? Or that's seconds, actually.
Good. I actually introduced that wasp into your house, and it's been instructed to sting you if you get the wrong answer. So, no, I'm just. All right, I'm just kidding. I hope you can. If you need to take care of that, I understand. But usually, if you leave them alone, they'll leave you alone. I think, right? Wasps are kind of assholes, though. Okay, how many of you got 1.5 times 10 to the 7 seconds? You got it, Catherine. You got it, Will. Sarah, what'd you get?
I got it.
Oh, killer. Did everyone get it? Because that would make, Joel, did you get that? Holy shit. Life's never been this good to me. Okay. Let's convert that to years. Will, help me. Help me convert 1.7 times into the 7 seconds to years.
All right. So, whole dimensional analysis, I guess.
I'll start by writing your number down.
1.5 times 10 to the 7th.
Division bar.
Division bar. Seconds on the bottom. Year on top. And then 3.15 times 10 to the 7th on the bottom and 1 on top.
Good. Punch him in. What do you get? Everyone's looking at the wasp.
0. Let's see. 0.
Approximately what?
Approximately 5. 0.5. Yeah.
Half
Half
a
a
year.
year.
That's our answer. Now, do you guys want to see something slick? That was a bit of work, wasn't it? Hey, Evelyn. You're my proportionality guru.
Oh, am I?
Yeah. Evelyn, I want to show you how we could have done this problem a lot faster. I'm going to teach you guys why proportionality arguments are so powerful. Uh-oh, she's getting dive bombed. All right. Normally people sharing their animals is a fun experience, but this is the first one where a bit of danger is involved. I kind of like it. Okay, so, especially because I'm not the one about to get stuck. Evelyn, suppose I wrote out p squared is equal to 4 times pi squared times a cubed over g times the total mass. What if I had tried to write this as a proportionality argument? In part B, what factor did we change in this equation?
The M total?
The M total went from the mass of the sun to how many times the mass of the sun?
4 times the mass of the sun.
How would I write this as a proportionality argument in that case?
P squared is proportionate to...
You can do it.
4 times m.
4, you only leave behind the things that vary. 4 doesn't vary. Pi doesn't vary. Forget about that shit.
M total.
M total's not on the top.
1 over m total.
There you go. That's the proportionality argument. Wait, you're not done, Evelyn. Now do it the same way we did the last problem. What do you sub in for m?
4. 1 over 4.
P squared is proportional to 1/4. Take the square root of both sides. What do you get?
P is proportionate to 1/16.
False.
The square root of 1/4.
Which is what?
1/2.
I'm getting it.
That's right, Evelyn. Say it again.
1/2.
Killed it.
The new period is half the old period. You could have done that in 2 lines. Do you need to take a moment to deal with the WASP? I feel bad.
My sister just killed it. We're good.
Yay. Okay.
Yay.
It was long. Sorry, that was really distracting.
No, some people are really allergic. You can get messed up by those things.
I hold it up.
So I'm glad you've got the enforcer there to take care of business.
It's been helping me a
Did
lot.
anyone see I'm afraid that during all this WASP drama, you guys might have missed my cool point. What was my cool point? Did anyone understand my cool point?
If we understand how to do the math, we can just do a shortcut.
If you understand proportionality arguments. That was my pitch for why proportionality arguments are powerful. But yeah, kind of what you said, Joel, okay? All right, let's move on. We got to keep moving here. I'm reevaluating my plan. My plan is we're going to try to work on one more, and we're going to incorporate the rest into the lecture. And yes, I will give you a little pause before lecture starts. At least I think I will. Oh my God, it's 11:49. We can do a couple more bits here, okay? We can do this. What's the next problem in the sequence, Laura?
Number 57D.
57D. Okay, so let me get set up and then we'll start doing this. We're going to do as much as we can. All right. Can I erase everyone?
Yep.
Chapter 4, number 57D. What's the title of this one?
Using Newton's version of Kepler's third law.
From now on, I refer to Newton's version of Kepler's third law as NK3 because I don't feel like saying that a whole bunch of times. Okay, what's part D ask?
Calculate the combined mass of Pluto and its moon Charon from the fact that, how do you say it, Charon?
Sharon.
Yeah, orbits Pluto every 6.4 days with a semi-major axis of 19,700 kilometers.
I'm going to refer to the combined mass of Pluto plus mass of Charon, as the total mass of the system. My abbreviation is M subscript tote. What was the period again?
6.4 days.
And what was the semi-major axis of orbit?
19,700 kilometers. So we have to make that into meters and then the days into seconds?
That's right. So Laura, why don't you show them how it's done? Let's put kilometers into meters.
Okay, so 19,700 kilometers multiplied by the division bar. Kilometers on the bottom, meters on top. I should know this.
You should.
But
Kilo. Kilo.
Oh, 1,000. 1,000 meters is 1 kilometer.
Do the math in your head. What does that turn out to be in scientific notation? Make it 19.7.
19.7 times 10 to the 5? No.
Do better.
Okay. 7?
Do better.
8? I don't
Look.
know.
Your decimal point is there, correct?
Yes.
So count.
Oh. So 6
And the units?
meters.
All right. Shay, I'd like some more expert opinions here.
Oh, why are you asking me then?
Because for better or worse, you're our expert. Okay, so 6.4 days to seconds. Go. Shay,
You're
are you
muted.
Shay, you're muted.
6.4 days to seconds.
Yes.
Okay, 6.4 days times and then division bar. And then days on the bottom, seconds on the top.
Do you know how many seconds are in a day?
No, not offhand.
So why don't we go to something else?
Hours.
Okay.
Minutes.
And then we'll go from hours to what?
Seconds.
Quiet on set, please. What's that? Could you say
You
that
want
again?
to go to minutes or seconds?
You tell me. You're the boss.
Screw it. Let's do minutes because I'm not that smart.
Okay. And then what?
And then, yeah, another division bar and minutes on the bottom, seconds on the top. And there we'll go.
Now the numbers.
All right. So is it one day, 24 hours, 1 hour, 60 minutes, and 1 minute to 60 seconds.
Punch them up.
Two 18.4.
Say that?
218.4.
No way.
I screwed that up. Wait a second.
Yeah, you had.
Yeah, I'm an idiot. Oh, yeah, I multiplied it. Oh, yeah, I'm stupid.
No, multiplying is right, but 218 sounds kind of low, doesn't it?
21.
21 sounds even lower. Shay,
2,184.
Shay, just multiply 6.4 times 24 times 60 times 60.
I know how to do it.
That's a total of 9 keys plus an equal sign.
Oh, sweet Jesus. 552, 960.
All right, how do we say that? Let's round it to like 3 sig figs.
3 sig figs. 553 times 10 to the.
No, it's less than a million. How about 553,000? Does that
There you
work
go.
too? Okay.
Yeah, 553.
All right.
Oh, that's right. Less than a million. You don't want whatchamacallits.
Well, you could, but I just want you to be able to talk numbers like a normal number talker. 553,000, not 550,000. That's human calculator speak. All right. All right. I think now we're going to use a variation of Newton's version of Kepler's third law. Let me write it down for you. I'll be introducing this in class today. We're kind of a little bit ahead of ourselves here. Okay. First of all, does everyone have that before I erase? Because I need more board space for what I'm about to do. All right, got a thumbs up from a few of you. Hold on. I can only see a handful at once. Ah, hold on. I'm having some difficulty with my lifestyle here. There we go. Okay. I got thumbs up from everyone, right? I'm erasing. Wolfgang in the house. Let's get that kitty on the calculator. Okay. Here we go. Remember those numbers for me. When we rearrange NK3 solved for mass, we get the following equation. The total mass, the mass of Pluto plus the mass of Charon, is equal to 4 times pi squared times a cubed divided by g divided by p squared. Now we will plug in some numbers. That, by the way, I got by rearranging the previous formula, but I'm skipping the algebra for now because that's not interesting. The total mass will equal 4 times pi squared. What do we get for our distance? 19.7 million meters, right?
Yes.
Cubed. Divided by 7 times 10 to the 11 meters cubed per kilogram per second squared times 553,000 seconds squared. I probably should have put my units in red, but I'm kind of short on minutes here. Now, Casio people, I will show you first. Do you want to see a walkthrough on my calculator?
I think I'm good.
Oh, yeah?
I think. I'm not super confident, but
Alba does.
go ahead.
So if Alba does, I do. So we're going to do both
Will
calculators.
does too.
We'll find out in a second if you got it right, okay? Let's
Okay.
start Casio style. 4 times pi squared times 19.7 exp6 shift cube divide by 7 exp negative key 11 divide by 553000. I'm going to have to square that and then equals. Let's try it on the phone calculator. This is going out to the Pan eCal folks, provided my thing works this time. Yep. Okay, Pan eCal people, are you ready?
Yep.
4 times pi squared times 19.7 exp6 caret key cube close parentheses divide by 7 exp minus 11 divide by 553000 square key. equals. That's what you better see. Got it, Evelyn, huh? How'd you do, Sarah? You get it?
Yeah, I'm good.
Awesome. Catherine, Will, Cameron, Alba, Jose. Jose got it. All right. What's my final answer?
1.4 times 10 to the 22. And is it kilograms?
Excellent. Box it up. Okay. This is a real hard homework, not for several different reasons. In any of my classes, when we get to this stuff, it represents a little step up in terms of complexity, so people always get a bit stressed. Also, I didn't quite get to all of the formulas in my lecture, so that adds to some misery as well. Thank you. Command decisions. We are going to do E during lab. Cancel out F. We'll skip F, okay? We are going to cover 47 in lecture. We will cover 58 A and C in lecture. 57E will be our lab. That's the plan, okay? So why don't we do this, guys? Let's take a pause. Let's take a breather, because I think you guys could use it. We're a little behind schedule, but screw it. Take 5 to 10 minutes to relax your brain, and then we do some proper lecture. Everyone like that plan? All right. You like the breaks, right? The breaks help? Yeah, all right. Okay, will someone remind me to record, Shay? I'm going to pause it.
Yes, I promise I will.
All right. I'll see you guys in about 5 to 10. Hi.
News is Case Keenum went 11-3 a few years ago with the Minnesota Vikings. And I believe the Cleveland Browns roster right now offensively.
We ready to do this? Okay. More calculations, more laws of gravity, more than you ever wanted to know about the forces of nature. Let's get out our slideshows. At the end of our last lecture, we learned that Isaac Newton had discovered the law of gravity, in which he had deduced that gravitation is a force that is caused by the masses of objects. And it also gets weaker the farther apart they are and stronger the closer they are. How did he come up with such a law? Let's take a look at the internet. If we go here to Google and we type the name of Isaac's hometown of Woolsthorpe, England, the very first picture that comes up is a picture of Isaac Newton's ancestral home, which still sits there today with an apple tree in the foreground. And it is said Isaac Newton returned home after college because the bubonic plague. Actually, the story of Isaac Newton is kind of similar to the story that we have today. And the way that we're being ravaged by the coronavirus and everyone's got to be home confined, during Isaac Newton's schooling at Trinity College, where he was a subpar, lackluster student, supposedly, the bubonic plague struck London and nobody understood what was causing it. And all of the students and people fled London for the countryside. And Isaac went to stay at his parents' house in Woolsthorpe, England, at this country house here. He brought with him the works of Johannes Kepler and Galileo and other greats from the annals of science, even Aristotle and Plato. And he read these works and he did some thinking. And basically, one day he writes in his journal that he was occasioned by the fall of an apple. He saw an apple fall from a tree outside. And he said that it had a profound effect on him because he realized that the same force that drags that apple to the ground is the same force that keeps the moon in its orbit around Earth. So he connected the forces that he sees here on Earth with the same forces that were governing the cosmos. And that was a big intellectual leap because Aristotle had claimed that the laws that governed the heavens were somehow different than the laws that governed Earth. And this was a big insight that he had. Now, how he went from there to the law of gravity is a little bit of history that I don't have time for. But as I've mentioned in a previous lecture, he wrote his law of gravitation in a different way than we write it today. Sorry, my marker here. When Isaac Newton wrote his law of gravitation, he wrote it as the force of gravity is proportional to the product of the two masses and inversely proportional to the distance between them squared. But remember, if you want to transform this from a proportionality symbol into an equal symbol, you need some extra information. In the MKS system of units, masses are measured in kilograms. Please remember, students, that nature did not invent the kilogram. Where's my kilogram for dramatic effect? Oh, here it is. Human beings invented the kilogram. Human beings decided that this should be a standard unit of mass, and masses should be measured in this quantity. This is a human invention. We decided kilograms should be this much matter. The distances are to be measured in meters. And once again, human beings invented the meter. We decided, for some historical reason, that this ruler here should be a standard unit of length that we use to measure out distances in space. This is our invention. We imposed this concept on nature. And forces are to be measured in newtons. But remember that a newton is a kilogram times a meter divided by a second squared. And because we invented the kilogram and the meter and the second, we therefore also invented the newton. Do you want to know what we didn't invent? We didn't invent gravity. Gravity was there before we were born, before humans came to be, before any life existed on Earth, gravity existed. Gravity is part of the machinery of the universe itself. Nature invented gravity, not us. But at some point, you've got to remember that you need to ask nature what her opinion of gravity is. You've got to say, hey, nature, if I have two 1 kilogram masses and they're separated by 1 meter, just how hard do you plan on tugging on these two things? That's not something that's up to you, that's up to nature. Isaac Newton did not know how to ask nature that question. He did not know how to actually calculate a force of gravity. He could only tell you how much the force would change if you varied one of the masses. In order to go from the proportionality sign to the equal sign, we have to perform some experiment that attempts to measure gravity. And to do that, we need to measure what's called the universal gravitational constant. That's the proportionality constant that tells you for this many kilograms, you get this much force. It's known as big G. and it has a value of 7 times 10 to the negative 11. Units are meters cubed per kilogram per second squared. Does anyone know who first measured the universal gravitational constant? He was a scientist that came maybe even 100 years after Isaac. His name was Henry Cavendish. And he performed a legendary experiment known as the Cavendish experiment. His original paper is quite interesting. He didn't title it, guess what, guys, I'm the first person ever to measure the gravitational constant. He called his paper On an Estimation of the Mass of Earth. He used it to measure the mass of Earth. That was his goal. Come on, show me this thing. Here's Henry Cavendish. Let's see if we can find his apparatus for gravitation. Here it is. He did this kind of interesting thing where he took 2 giant spheres made of lead. Okay, this isn't working. And the 2 giant spheres are suspended from something called a torsional pendulum. Here's a decent little picture of it here. Oh, come on. So what he does is, it's kind of amazing. He takes a very, very thin wire and suspends from that wire a barbell. They call this a torsional pendulum in physics. So you have a bar suspended from a wire. And he put 2 masses made of lead at the end of the barbell. And then he put next to them these very, very large spheres of lead, so dense and so massive that there's actually a slight tiny bit of gravitational attraction. And they're only going to get a small deflection. So suspended from the torsional wire, he puts a mirror. Now, I think he might have used candlelight because he did this in the 17 or 1800s. But today what we do is we shine a laser on that mirror. And if the masses get deflected, the laser beam also gets deflected by some large angle. And by measuring the angle, you can actually estimate what the force is between the 2 objects and then back calculate to get G. Kind of a genius experiment. The Cavendish experiment is still performed in physics departments all around the country today. It's a classic. And when he did this, I think we could probably even find his paper if we wanted to. Cavendish mass of Earth. Sometimes you can find it on Google. Well, he didn't, I don't know if he appreciated what he was doing or if he just, he was just more interested in measuring the mass of Earth because no one had done that yet. Oh, damn it. Once upon a time, I clicked on a link and it gave me the actual paper. It was kind of cool. Well, in any case, the upshot of it all was that he was the first person to measure the mass of Earth, but more importantly, he was the first person to ever estimate the value of big G. And with that, it allowed us to properly write the law of gravity as it was intended to be written. Big G times M1 times M2 is equal to the force of gravity. Now, in our previous lecture, last time, we calculated the Earth-Moon gravity. And we found a force of 2 times 10 to the 20 newtons. I would like to begin today by doing a comparison. Hey, Joel, I'm going to test your scientific intuition here, okay, buddy? What do you think is stronger if you had to take a guess? The force of gravity between the Earth and the Moon, or the force of gravity between the Earth and the Sun? If you had to guess, which would you say? Is the gravity between Earth and Moon stronger, or is the gravity between the Earth and the Sun stronger?
Earth and the sun.
Everyone else back him up on that? Or any differing opinions? Evelyn says Earth and
That's
Sun.
what I'd say, yeah.
Shay says it too. Everyone else doesn't care, or, okay. Well, let's find out if Joel is right. Let's
Is
calculate.
that,
Oh, yep.
so the reason I think that is because the sun's bigger than the Earth, and the
Well,
Earth
when
is
you say
than the
bigger, it
moon.
makes me think of physical size, Joel. Do you mean more massive than Earth?
Yeah.
Okay. Because gravity doesn't depend on size, it depends on mass, right?
Right. So like if the sun has a bigger mass, which has in my head has a bigger magnetic field.
No, no, no.
So it has
Magnetic
a
field that's a side issue.
bigger
Magnetic,
pull, like
forget
I don't
about the magnetic field. That's a separate force. Joel, here's the confound. A confound in science is when you have two competing variables. For the sun and the Earth, the mass of the sun is much more massive than the moon. But the distance to
right.
the sun is also greater. Right?
Yeah.
That tends to make the force weaker. All right. Well, let's just calculate it. That's how we solve the problem.
So just a thought is
Yeah.
the thought that the moon affects our tides. Does that make the moon's gravitational force stronger than the sun because the sun doesn't affect our tides?
That's a great point, Will, and that's a point that I was going to get to. Tides are caused by the moon, not the sun, right? And Will, aren't tides caused by
Correct.
gravity?
Yes.
So that would make you think the moon's gravity should be stronger than the sun's, doesn't it?
Right. That's what I was sort of leaning towards.
Okay, so it's Will versus Joel. Who has the greatest scientific intuition? We're going to calculate it now.
I'm going with Will.
Let's try it. The mass, we know the mass of the Earth, we know the force of the Earth-Moon gravity. We'll compare it. Let's find the force of gravity between the sun and the Earth. Okay, the mass of the sun is 2 times 10 to the 30 kilograms. The mass of the Earth is 6 times 10 to the 24 kilograms. I'll use red for the units, and I'll set up the force law down here. Sun and Earth force is 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of the sun, 2 times 10 to the 30 kilograms, times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by the distance between them. Shoot, what's the distance again?
Well, 150 times 10 to the 6.
What's the units?
And then kilometers.
That's not an MKS unit though, bud.
Oh, no. 150 times 10 to the 9th meters.
Very good. 1 AU is 150 billion meters. And we got to square that. Okay, I want to see everyone's calculator this time. Everyone's going to put their calculator up when they get the answer so I can see what you got.
I got 3.73 times 10 to the 22nd.
Evelyn, let me find your little face here. Could you say that one more time? Actually, wait, Evelyn, pause. I'm gonna, there's some laundry going on. I'm gonna close the door to the laundry room so I can hear you better. And close those sliding doors if you can too. Could you say that one more time?
3.73 times 10 to the 22nd.
Excellent, but 3.7s get kind of boring at this hour of the day. What if we just round that up hard to
4?
4 times 10 to the what?
22nd.
Units?
Newtons.
Newtons. Can everyone show me that on their calculators? Hold them up. If you didn't get it, you have to listen. This is something I make a big deal about when I'm in personal lecture. Yeah, I want to see those numbers. Good. I like to verify that. Jose, got to show me. If you're not getting it, Jose, we got to work with you.
Yeah, I didn't get it right. I had 2.25 to the 22nd.
2.25. Your mistake
Yeah.
was you just hit a funny button. Could you punch it all
Yeah,
again?
I don't think he squared. I don't think. Yeah, I had that for a
If he
second.
didn't square it, he wouldn't have gotten 22nd. You had 10 to the 22nd power?
Mm-hmm.
Did you use the pi key or did you use 3.14? I see it. Thank you, Will. Jose, can you just punch it again, please?
Yeah.
No child left behind. That's what they call this, right? Okay. Alba? Catherine, Cameron? What the crap's going on there? You can't hide from me. You can't hide from me, Catherine. You show me that calculator. Yay. Okay, I love it. I love it.
Wait, did
hide
you
from
say
me now.
pi?
There's a pi key. Yeah. Which one are you using? You're using my calculator,
Oh,
right?
because I.
Just hit the EXP.
Yeah, but I'm.
Watch.
There's no pi on this problem.
Oh, yeah, you're right. Sorry. There's no pi in this problem. I'm sorry. There's no pi. Watch. Jose, watch.
Okay.
7 EXP minus 11 times 2 EXP 30 times 6 EXP 24 divide by 150 EXP 9 square. Oh, you forgot to hit equals, dude.
Oh, equals first.
No, equals at the end. You square and then equals. You squared it, and when it showed you the square, you thought you were done. You had to hit equals, Jose.
Okay.
You just forgot to hit your equals at the end. Punch it again. Okay, who was the greatest scientist? Was it Jose or was it Will? I'm sorry, was it was it Joel or was it Will? Who was right? Not Will. Joel was correct. Joel, the gravity, you are going to be rewarded with some more work, okay? You're going to be rewarded with
Yay, more math.
What's
You're lucky,
My
Will.
girlfriend was in the armed services, and she told me the #1 rule in the military was never volunteer for anything, right? Does that sound familiar?
Yeah, you always get voluntold.
That's what Navy stands for. Never
Oh,
again
really?
volunteer yourself.
Wait, say it again.
Mm-hmm.
Never what?
Navy. Never again volunteer yourself.
Never again volunteer yourself. Okay, it's good to know that translates to the Navy as well. Never again volunteer yourself. Okay, so without using a calculator, Joel, I want you to tell me, since you were correct, how many times greater is the force of gravity between the sun and the earth than the moon and the earth? Can you do that in your head?
Let's see.
Let's do it together. Ready? We have 4 times 10 to the
200.
Say that?
200 times.
Excellent. 4 divided, I want to show everyone how Joel did that. 4 divided by 2 is 2. 22 minus 20 is 2. It's 200 times greater. That's right, Joel. Hey, Will.
All my mortar,
Oh, yeah.
my mortar training math paid off.
Okay, that's great. Well, it is paying off because you're getting your education for free. So that's one thing, right?
That's right.
All right. Will, never again volunteer yourself. I've got a funky question. Will actually really stubbed his toe on a profound conundrum here. If the force of gravity between the Earth and the Sun is 200 times greater than the force of gravity between the Earth and the Moon, then Will, what the hell is up with tides? Because I thought tides were caused by the moon, like you said, but the moon's gravity is 200 times weaker than the sun's gravity. That's pretty strange, right?
Yep.
So how does
It's
that
also
work?
closer.
Right, but didn't we accounted for distance in our calculation, didn't we, Will? We plugged in the distance to the moon, and we plugged in the distance to the sun, and it still turned out that the sun's gravity was greater. You want to know why? Because the sun's mass is a fucking 2 followed by 30 zeros. And that's like a big ass number. Right? So even though the moon is closer, it doesn't matter that the moon's closer because the sun's mass is a 2 followed by 30 zeros worth of kilograms. But the thing that we now have to understand, Will, and I don't expect you necessarily to know the answer, I want to get your noodle cooking here, is why the hell is the moon causing the tides? Well, tides are caused by gravity. They're not caused by magnetism, right? They're caused by gravity. That's what I was told. How can it be that the moon's causing tides with gravity when its gravity is weaker than the sun's by 200 times? That makes no sense. Or maybe it's that we don't understand the tidal force. Maybe the tidal force is more subtle and sophisticated than we were prepared for. Let's take a few notes on the tidal force, and then we're going to work in that homework problem, okay? Can I erase everyone? Is everyone cool here? Here I go. Okay, so let's do a little set of notes on the tidal force. And I'm going to present this to you guys as a set of bullet points to kind of summarize my thinking. So first bullet point. Tides are caused by gravity. But, ... there's a but. The so-called tidal force does not equal the gravitational force. It's not the same thing. There's a nuance. There's a difference. Tides are caused by gravity, but the tidal force does not equal the gravitational force. Here's what the tidal force does equal. The tidal force is a, wait for my $10 phrase here, a differential force. And I want you to underline the phrase differential force. That's key. The tidal force is a differential force that acts across an extended body. To use the language of mathematics, the tidal force is a delta force. A delta force caused by the difference between the force on the front of a body minus the force acting on the back of a body. It's a delta force. The front force subtracted from the back force, caused by a small change in distance.
So it's like drag.
I wouldn't say drag. I would say it's a
Or like
gradient.
resistant. Like
No.
it works against.
No, I don't.
Okay.
I don't like that either, Joel, because I want my language to be precise here. I could say the tidal
Okay.
force is a if you want to say, don't say drag, you say gradient. Let's say that as well.
Hey, Brandon, I don't know if it's my computer, but it's super blurry. I can't read what you're writing.
All right, let's see what's going on. On my screen, it looks crystal clear. Joel, does my writing look clear or fuzzy to you?
It's fuzzy.
Fuck. Maybe that's my internet. Is it fuzzy for you, Evelyn?
Yeah, it's fuzzy.
Shit.
It's always fuzzy.
It was trying to focus on you. The
Was it my
stupid thing-
focus or was it the internet?
It's your internet, yeah.
I can pretty much see everything other than like what like is underneath like the two big F's. I can't read the what it said.
Okay. It's always blurry? That's sad
No,
because
not
it's,
always.
I can read it
Just
now.
right now.
I'm uncomfortably close though. I've got like this much wiggle room, so we'll have to work on this.
Aw.
No, you can back up. It's just the way that your stupid camera works.
I know.
I
By the way, I bought a
as you
GoPro.
can
There's a way
see.
to use your GoPro. I'm going to try to use the GoPro as a camera. I'm going to figure this out some point. I'm just incredibly lazy. That's the problem. Does anyone know what I mean by the word gradient? I think the kids today would call it a fade. Okay, that's what we would call it, a fade. Let me show you. Let me show you a black to white gradient. This is what a gradient would look like if you fade from black to white. A gradient is actually a mathematical concept. If you guys imagine white having a value of 100% and black is having its value of 0%, just like intensity of pixels, you can see that the numbers or the intensity of the pixel will vary from 100 to 0 as we go white to black across the screen. There are other types of gradients as well. A gradient is actually a mathematical construct, but it can appear in different locations. Has anyone here had calculus? I don't think so, right? Oh, Evelyn. You took it back in the day? I had to take it in high school. For those of you who have had calculus, let's add one more tidbit. This is something that it's probably good to hear even if you haven't had calculus, but I'm letting you know this is a advanced thing. The tidal force is the derivative of the gravitational force. And because it's the derivative of the gravitational force, the tidal force is actually proportional to 1 over the distance cubed, not 1 over the distance squared. And this is why the moon's gravity is weaker than the sun's, but the moon's gravity has a bigger gradient of force. I'm going to explain that in a cartoon way because that's probably not clear to everyone. Just because I put all those bullet points up on the board, that doesn't mean that you understand tidal forces. So we're going to make a little cartoon together, which I think is going to help. I want to wait until everyone's caught up before I erase. Everyone feeling good here? Can I erase? I'm doing it. All right, let me back up. There's too much stuff. It's all spilling out everywhere. Okay. Let's use use the Earth and the Moon as an example. Let's draw a cartoon picture of what's happening when we mess around with gravity. Am I using the right camera? I didn't check that. Yeah, I am using the right camera. Okay. So here's the Earth, and here's the Moon. And let's draw the distance between them center to center. The distance from Earth to the Moon is 384,000 kilometers. So the Moon is about 400,000 kilometers away. The radius of Earth is 6,400 kilometers. Class, what is the diameter of Earth? Let's start off nice and slow here.
12,800.
Evelyn, what percentage of the Earth-Moon distance does the diameter of Earth comprise? You know how to do that, right?
Can you say that one more time?
I want to know, you agree that the Earth's diameter is smaller than the distance to the Moon, correct? So I want to know what percentage of the Earth-Moon distance is the diameter of Earth.
You divide 384,000 by, or nope, never mind.
Upside down, right? Percentages are less than 1, correct? Right?
Yeah.
So we divide 12,800 by 384,000 kilometers. Go ahead and punch that into your calculator, Evelyn. Everyone else do the same thing. Everyone punch. Everyone punch. If you want to learn, punch.
0.03 repeating.
What is that as a percentage?
3%.
Very good. The front side of Earth is 3% closer to the Moon than the back side of Earth. Now, I want you all to imagine something with me. I want you to imagine that I invented the world's largest cheese grater. It's a cheese grater capable of slicing planets up into planetary cheese, okay? And I'm gonna take this cheese grater and I'm gonna make a thin slice of Earth provolone right here in the front towards the Moon. This slice is so thin, the mass of that Earth cheese is so thin that if I calculate the force of gravity between this little cheese slice and the Moon, I'll discover that the force of gravity is only 40 newtons because the mass of that slice is very, very thin. Now this is the front slice. Now I'm going to take a second slice. I'm going to slice an equally thin slice of Earth cheese at the back side of Earth. This slice of cheese on the back is so thin and its mass is so small. Will the force of gravity on this slice also be 40 newtons? If it is the same mass, what do you think, Will? Will the force of gravity be the same if the mass of the slice is the same?
Yes.
No.
No.
Why not?
50 chance.
Why will the force of gravity on the back slice not be the same? That's okay. We're learning. Laura, do you know?
Oh.
Oh, who knows?
Well, if it's the same, did you take the same amount from the front and the back?
Yes, I did. I did take.
So it wouldn't change it. Wouldn't change anything.
But I think you're forgetting about something, Will, and that is if you go to our law of gravity, the law of gravity doesn't depend upon one factor, mass. It also depends upon distance, doesn't it?
Oh, so yeah, you change the distance.
The slice is the same mass, but it's further back. How many % farther back is it?
3%.
How many times will the force of gravity drop?
3 times?
False.
I don't know.
Evelyn, can you tell me what factor the force of gravity will change?
1/3?
No.
Smaller than that?
It goes as the distance squared. If the distance varies by 3%, the force of gravity will vary by 9%.
Okay.
Whatever, okay. It's farther away, so the distance is weaker, right? Let's say the force of gravity on the backside is 30 newtons. Therefore, Earth is feeling a shearing force, a tidal force, which is the difference between the force on the front side of the planet minus the force on the back side of the planet. In other words, Earth's change in force, its delta force, will be 40 newtons minus 30 newtons, which equals a 10 Newton differential. Exclamation point. Let's imagine that you're Earth. Let's imagine what this differential force will actually feel like. It will feel like you're a teddy bear which is having its 2 arms tugged apart by a child. Because the force on the front side, being stronger than the force on the back side, this is the front force, is stronger than the back side, means that from an Earth-based perspective, you're feeling 10 newtons of shear stretching you apart. And this is why the moon doesn't cause 1 high tide per day, but it causes 2 high tides. One of the high tides is in the direction of the moon, and that makes sense. But you know that there's a high tide that points opposite the moon? That's a little bit tricky to explain unless you think of the Earth as being pulled side to side. I should mention to the class, not only does Earth experience water tides due to the gravitational force of the moon, but Earth's atmosphere also bulges in the direction of the moon. And here's a creepy one. The ground rock underneath your feet deforms as well towards the moon. It's lifted up by about 3 centimeters due to the moon's gravitational force. There's actually rock tides underneath your feet. The ground rock underneath your feet is bulging towards the moon. Pretty badass.
Yeah, I was gonna ask, like, I was just thinking about like molten lava, like, you know, is that force the same on that as well?
So in the case of Earth, the bulge in 3 centimeters out of the moon's 6 million meter radius is not sufficient to add enough geothermal energy to create internal heating, not much. However, I should say, Shay, that is true in other places in our solar system. So since Shay brought it up, one of the most volcanically active moons in the entire solar system is a moon of Jupiter known as Io. Io is the same exact size as our own moon, but unlike our own moon, it is covered with pits of active volcanism. Do you guys see this giant, or first of all, Io looks fucking crazy. It's so volcanically active, in fact, that it's constantly spitting out fresh sulfur dioxide that makes these big frozen orange and yellow sulfur pools all around the volcanoes. When we did a flyby of Io, we actually saw some active volcanism going off its surface. See that yellow stuff? That's all sulfur dioxide from all those black pits are all volcanoes. It turns out that what makes Io such a volcanically active world is exactly the thing that Shay was just talking about. It's called tidal heating. And basically what's happening is, sometimes they call it tidal friction. What's happening is as Io is orbiting around Jupiter, the tidal forces of Jupiter are so strong that they actually bulge Io into an egg shape aligned towards Jupiter. And as the egg tries to rotate around, the bulge keeps whooping and warping and whooping and warping. And it makes the internal moon so hot that it starts becoming molten in the interior and giving off volcanism. So Shay, that's not happening to the Earth because the moon is not as massive as Jupiter. But if you continued to increase the mass of your object, yes, that would actually happen. In the case of Earth, it's not enough. Not much anyways.
Right.
Now, Will, let me find your face here. Will, suppose you were a pesky student. He's having a snack. What if you were a pesky student, Will, and you wanted to keep bothering me? What if you weren't satisfied and you said, okay, Brendan, okay, differential force, got it, shear force, got it. But didn't you say the sun's gravity was 200 times greater? Why isn't this happening with the sun? Shouldn't this happen with the sun? Yes, but it's not the same. And maybe my cartoon could help explain why. Let's try doing the same argument for the sun instead of the moon. The diameter of Earth is 12,800 kilometers. The sun, however, is 150 million kilometers away. Evelyn, what percentage of the Earth-Sun distance does the diameter of Earth comprise?
3%.
Huh?
3%.
Fuck no. The moon is 400,000 kilometers away. The sun is 150 million kilometers away. We got to do it again.
Sorry.
That's
I thought
okay.
you were. It would be divide that by.
Can you give me that as a decimal?
That would be 0.000085.
Let's make it 9. 0.00009. Is that it?
Yeah.
What's that as a percentage?
That's like like 1/1,000,000th of a percent.
Not quite. First, just give it to me as a percentage. How do I turn this into a percent?
But what? It's 1 over it.
No, you move the decimal place twice.
Okay.
So?
I'm not sure. It's just.
Hey, Evelyn, Evelyn, what is 0.5 as a percent?
50.
Right?
Oh yeah.
Could you do that for this number now?
It would be like 0.009. So like.
Now let's focus on how to say that. How do we say this number? That's not 1/1,000,000th.
A 100th.
No. Let's do it together. Which place is this?
Tens.
This one?
Ones.
Huh?
The ones?
No. This is the ones. This
Oh,
is,
right.
This is a 10th.
Yeah.
This is a 100th.
100th.
This is a 1,000th. So how do I say this?
A 9,000th. 1/9,000th of a percent.
Very good. Or more elegantly, 9,000ths of 1%.
Okay, yeah.
Same thing as 1/9,000th of a percent. Well, no. It's 9 parts out of 1,000 of 1%, right?
Yes.
This number means 9 over 1,000 times 1%. It's less than a percent by 9 parts in 1,000, right?
Yeah.
Pretty fucking tiny percentage, right?
Yeah.
Okay. Let's imagine that on the front side of Earth, the sun is now tugging with a force of 400 newtons. Do you agree that's stronger than the force that the moon was tugging on it?
Yes.
The backside is now being tugged only by 399 newtons, because there's only a 0.009% variation across the diameter of Earth. So what is the tidal force as caused by the sun?
Just one Newton.
So if you think about it, it is possible to say two things that sound contradictory, but are in fact not contradictory. The force of gravity between the sun and the Earth is at all points greater than the force of gravity between the moon and the Earth. But the moon's tidal forces are greater than the sun's tidal forces. Can you guys see that now? It's okay that the sun's gravity is stronger because the tidal force is not the same as the gravitational force. It's a gradient of force. And the diameter of Earth is a smaller percentage of the Earth-Sun distance. In fact, I got some secret surprise for you. As any good Rhode Island caw hogger ought to know, it turns out that the sun's gravity does affect tides by a small amount. Twice a month, fishermen know about what are called spring tides, unusually powerful tides that occur during full moon and new moon that are caused by the sun giving an extra kick to the gravity of the moon and creating especially high tides. Twice a month, we also occur neap tides. Neap tides are wimpier than average tides, caused by the fact that the sun is at a 90-degree angle to the moon, and its tidal forces help to reduce the strength of the moon's tidal forces. So the sun's gravity does affect tides, but at a secondary or tertiary level compared to the moon. That's pretty interesting, wouldn't you say? By the way, you can actually see variations in tides if you look up Narragansett Bay. This sometimes works and sometimes doesn't, so I'm not going to try too hard, but let's try tidal variation Narragansett Bay. Let's see if we can bring this a little closer to home for us. Sometimes you can see a chart with the strength of the tides. This is each day as Earth spins. I'd like to see over the course of a month. Let's go to the third. Clear. Let's go to a previous month. April. Oh, come on. Oh, shoot. I'm sucking. I'm sorry. Won't let me go to the first. It'll only give me a 2-week period. Huh. Well, it's only going to be good if we can see it for a month. This is just a single day.
Go back to the Google search and put monthly.
Yeah, I found a really nice one a semester ago. Sometimes I can, there's some ways, this is over 100 years. It'd be nice to see it over just 1 month. That's what I want, 1 damn month. Okay, I'm not gonna, I think it's the Narragansett Bay Commission or something has a little machine, but I don't have time to doink around with this because But what if I type 1 month? Monthly. Okay. Maybe I can work with that. Oh no, that's a single day. Okay. I should have prepared this beforehand, not after. One day I clicked and it was the first link and it was really elegant, but that was not what happened today. You know what I think we should do instead that would be a better use of our time? We should answer that homework problem on tides, right? Laura, can you read that one for me? Which number is that? We're going back to the homework for a minute.
Let me see, was it number 47, the head to foot tides?
Okay, everyone, let me just take a second here. We're going back to homework 3. This is chapter 4, number 47. It's called head to foot tides. Okay, and read it up for, wait, hold on, I gotta get my thing here. Okay, Laura, go.
You and Earth attract each other gravitationally, so you should also be subject to a tidal force resulting from the difference between the gravitational attraction felt by your feet and that felt by your head, at least when you're standing. Explain why you can't feel this tidal force.
Okay, I'm gonna make my picture a little better. On the left side of your page, draw a big old Earth, and then draw a human standing on top. Here's the radius of Earth. By the way, does anyone know the answer to this question based on the discussion we had? Why can you not feel a tidal force acting across your body?
We're too small.
Compared to what? A chihuahua?
No, to the Earth or the gravitational pull.
Okay, so flush it out a bit, Shay. We're too small compared to the Earth, so what? Or is that it? We're just too small, full stop.
We're not big enough to have any type of I don't know the word I'm looking for.
Tidal force?
Yeah.
What would the tidal force look like on a person? I want to make sure you guys can understand that. How does the Earth cause a tidal force on a man? What would that look like?
Would it be a sideways force?
False. It's an up and down force.
So like our head being ripped from our feet?
Yes. It's the difference between the fact that your feet are closer to the center of Earth than your head is. Let's draw that in, okay? There is a force acting on your feet. We will call that force F sub feet. Technically speaking, your feet are a little bit closer to the center of Earth than your head. There should be a second force, F sub head, acting on your head, and the tidal force would be the difference between the force on your feet minus the force on your head. What's the typical height of a human being in meters? Huh? Say it one more time.
2.5.
Oh, hell no. Look, I ain't the tallest drink of water on planet Earth, but this is 2 meters right here, Evelyn, if that was you.
Oh yeah, never mind.
I'm about 1.75 meters tall, right? I'm almost 6 feet. My ex likes to point out that it said 6 feet on my driver's license, but you're not really 6 feet. You're actually 5'11". That's what she said to me one day. Okay, fine. 5'11 and a half. I'm about 1.75 meters, okay? So a 6 foot tall person is about 1.75 meters. So sometimes if you want to round to 1 sig fig, I'm a little closer to 2 meters than I am to 1 meter. So people say the average height of a person is close to 2 meters. All right? How does that compare to the radius of Earth? What's the radius of Earth in meters, Joel? You seem to be good.
6,400 kilometers, or 6.4 times 10 to the 6 meters.
6.4 million meters. So Joel, what percentage of the Earth's radius does a human being comprise?
Super, super small.
Let's put it down.
1.
2 parts out of 6 million is 1 part in 3 million, right?
Yep.
It's a 1 part in 3 million ratio. Two divided by 6.4. Hey, Evelyn, what is that? Where's Evelyn? I'm going to keep picking on her until she gets her percentages right. Where are you? I'm looking for you. Can't hide from. All right, there you are. Evelyn, 2 divided by 6.4 million. What do you get?
2 divided by 6.4. Oh gosh. Okay. This would be before you put it into a percent, it's 0.
Here,
0.
let's do 3 times 10 to the minus 7.
Okay, yeah.
So what's that as a percentage?
It would be
Add 2 zeros.
that would be 3 times 10 to the -5th.
How do I say that in plain English?
That's a million.
Nope. Count with me. What place is this?
The 10s. 5s.
No.
I'm so bad at
I know. Guess what, Evelyn? Everyone's bad at this. I got some news for you. You're all bad. And it's my job to make you better. And this is how I'm going to do it. Okay? So, Evelyn, when you move decimal points, you're going by powers of 10. So if this is 1/10, what is this?
1/100th.
What's this one?
1,000th.
What's this one?
10,000.
What's this one?
2,000.
Sorry?
1,000. 100,000.
So how do I say this in English?
300,000ths. 300,000ths of a.
Thank you. 300,000ths of a percent.
Sorry.
That's all right. We're learning. That's how learning works. Okay? 300,000ths of a percent. So what's the answer to the question? Shay, let's get back to your answer.
We're tiny.
In comparison to?
In comparison to?
A chihuahua. An aardvark.
The Earth. The Earth.
The radius of Earth.
The radius of the Earth, right.
And so therefore,
there's really not that big of a difference between our feet and our head compared to the radius of the Earth.
Hallelujah, Jesus. Okay, let's put that into plain English together, okay? I'm going to erase and I'm going to write a paragraph and you're going to copy me. A person will not feel a tidal force from Earth across their body because, that was a lame because. A person will not feel a tidal force from Earth acting across their body because the 2-meter height of a person is millions of times smaller than the radius of Earth. Therefore, let's use a fancy vocab word. Professors love it when you regurgitate their fancy vocab words. Therefore, the differential force between the Earth and your feet the differential force between the Earth and your feet versus the Earth and your head is essentially but not quite zero. Technically speaking, a tidal force does exist from your head to your feet, but the intermolecular forces that make up your bones and your flesh are probably much greater. That would not be true if you took a trip to an exotic object like a white dwarf or a neutron star. At the surface of a neutron star, I suspect tidal forces would be capable of tearing your body apart atom by atom, and it would be quite unpleasant. Will,
I got a question.
Yeah.
Okay, so if the tidal force is so insignificant to the human body, is there any scientific evidence that tidal force caused by like the moon induces labor and things like that in women?
No, not at all. Because if we had a little more time, Will, and we plugged suppose I took the average mass of a woman, which might be 90 kilograms, okay? And I calculated the force of gravity between a woman and the moon. I would get a value in newtons. But if you then calculated the force of gravity between a woman and a dump truck parked outside, you might discover that the force of gravity between a dump truck and that woman was actually slightly greater than the moon's. So I don't hear any kooks telling me that dump trucks are inducing labor in women, right? Nor are stone buildings. See, it's the moon, because the moon's magic. No. Now, there is a connection, I believe, between, just to get into it, I mean, it's an obvious fact that the cycle of the moon is 30 days and menstrual cycles are 30 days. And there probably is some valid evolutionary reason for that. For instance, maybe people were finding each other during moonlight, like during a full moon, it would be easier to find a mate than it would during darkness when we were some kind of proto-human, like a Neanderthal or something. So perhaps going back millions of years, there's a reason why menstruation cycles and the moon follow the same cycle. But that does not mean that the gravity of the moon is inducing labor, because the moon is sufficient. The moon's gravity on Earth is 2 times 10 to the 20 newtons. But if you plugged in a human's 100 kilograms, 7 exp minus 11 times 100 times 7e22 divided by 384 million squared, you get 3 times 10 to the minus 3 newtons. And that's probably less than the force of gravity between you and a dump truck you're standing next to. So if garbage trucks aren't inducing labor, the moon certainly isn't. But that's not an invalid question. It's an interesting question. Just how, one thing that it's hard for students to comprehend your first go through this is just how fucking weak gravity is. Gravity is a wimpy ass force. It has that 7 times 10 to the minus 11 in front of it. In fact, well, gravity is so wimpy that you really only start to notice it at all once you build a giant planet-sized rock worth of matter that you're standing on. And then suddenly you realize, oh man, I'm actually sticking to this thing. You know what I mean? But even if you were to travel to an asteroid, the gravity of a typical asteroid is so weak that you could literally jump off of the damn asteroid and achieve escape velocity. So it's just trying, we think of gravity as strong because when we fall on our face, it hurts. But we're forgetting that the mass of Earth is pretty significant. The moon's so far away that it's not going to have any, the intermolecular forces, the atoms that make up your bones, are much stronger than the force of gravity between you and the moon. So whatever chemistry is going on in a woman or a man when they do their things, that's overpowering the gravity of the moon. But a valid question. Let's check how we're doing here. 126. We're almost, but not quite there. I'm going to give you guys another break in a minute. But let's see. I actually kind of built in some time for us to do this slow and right today. Let's do one last little fun thing, and then we'll take a tea break. A quick thing, quick exercise. Let's remember what can I erase this, by the way? Did everyone have enough time to copy? All right, here we go. Jordan, would you mind giving it a little air co at 72? Thank you. We're starting to, I'm sweating like a pig in a Hawaiian luau, okay? All right, so Newton gave us 2 different concepts that can be combined. Newton gave us his 3 laws of motion. And the quintessential formula that describes Newton's laws of motion is the legendary formula F equals ma. That's Newton's second law. And probably the second law is the most important of them because that's the formula that explains what a force is and how it causes things to accelerate. Remember that the force here is just a general arbitrary force. It could be gravity, it could be magnetism, it could be the force of punching your little brother in the nose. Anything that pushes or pulls is a force. Newton also gave us his law of gravity. And the law of gravity is a specific force. It's a fundamental force caused by nature. And this law teaches us that gravity is induced by mass. It's the product of the 2 masses divided by their distance squared. Believe it or not, it is possible to combine these 2 laws to sort of add them together and to discover new truths about your own universe. And not only did Newton come up with these laws, but he used them to investigate the machinery of the universe. And he discovered some pretty interesting things. Now, one of the things that we really need to talk about is how he re-derived Kepler's 3 laws of planetary motion. But that's kind of a bit, that's a lot. So what I'm going to do is I'm going to give you a simpler example that'll give you the flavor of the feeling. And let's start by a problem that might have interested Newton, that of an apple falling to Earth. So what we're going to do in our sample question here is we are going to find the acceleration of an apple falling to Earth. And we're going to do this by combining these 2 laws. Let's start with the setup. So we'll draw planet Earth. with its radius of 6,400 kilometers. And I'd like you to remember that the mass of Earth is 6 times 10 to the 24 kilograms. Now we're going to draw an apple tree. And we're going to put an apple on the branch, and the apple is about to fall to Earth, and it will undergo some acceleration. Our job is to calculate that acceleration. What do you think the typical height of an apple tree is in meters? Keep in mind, class, I am not even 2 meters tall. I think I have 12-foot ceilings in this apartment. That's getting close to 3 meters. How do I do this here? This isn't going to be as impressive on my camera. There's my ducts. This is 3 meters here. I'm almost making it up to the top of my tin ceiling there, but not quite.
Maybe like 6.
6 meters? Oh my gosh. No. 6 meters is too high. This works well when we're all in the same classroom.
Probably about
3
4.
maybe.
3 or
4, yeah.
Apple trees are not as tall as pine trees. Actually, why don't we test, let's say it's somewhere between 3 and 4 meters. Let's see what the internet says.
Oh yeah, that's what I meant, like 4. Yeah, 4.
6 meters is taller than you think.
Yeah, right. Yeah, I lost perspective.
Standard size apple trees, let's do 20 feet. That's actually pretty tall. I bet that's about 4 meters.
It's between 6 and 7.
Holy
Just over
shit.
6, yeah.
Shay, maybe you were better off than I thought, huh?
Well, I am a psychic, so yeah.
This is your hustle?
We're not doing astrology, Shay.
I gotta say, guys, that I am shocked because I can remember when I went apple picking that you might need a ladder to get to the top of them, but it wasn't like pine tree tall, right?
Actually, yeah, I kind of have one up because I used to be an apple picker and do that stuff. So yeah, when I was a kid.
Wait, you used to be an apple picker?
I was an apple picker, yeah.
Wow. Okay, look, and so here we go. Here's some apple trees right here. 2 meters for a human. 3, 4, 5, 6. Okay. So Shay, you weren't kidding around. You know your stuff. All right, so let's go.
I remember I fell off of a ladder when I was up on top of one, and it was a long way. So I think that's what I remember.
Now I understand what happened. Okay. All right. Okay. So this is about 6 meters, 6 long meters, right, Shay? 6 very long meters. Shay, how does that compare with the radius of Earth in meters? What's the radius of Earth in meters?
It is.
What's your conversion?
Damn it. Joel always has it. Wait, it's right here.
Let's just do dimensional analysis. How many meters per kilometer?
1,000.
Okay. So what do you get?
Flippin' brain lock.
Punch it in.
Add 3 zeros to 6,400, Jay.
Yeah, 3 zeros to 6,400. So
not 6,400. Oh yeah.
Kilometers.
Yes. So what's my answer?
Do you want it in a scientific notation?
Is it bigger than 1 million?
Yeah.
Then yes.
No.
Yes, it is bigger than 1 million, and yes, I want it in scientific notation.
6.4 times 10 to the 6. That apple tree fall really affected me.
You've been personally burned by the force of gravity, it sounds.
I
have. So,
Post-traumatic stress from apple picking.
So let's rewrite these two formulas in terms of the apple tree. Let's see what happens here. What I'm going to do is I'm going to first say that there is a force. By the way, the mass of a typical apple is probably 200 grams, but it's not going to matter. Let's let M represent the mass of the apple, okay? The force acting on the apple will cause the mass of the apple, red M, to undergo an acceleration, which we are interested in calculating. And now I'm going to set this force equal to the force of gravity. The force of gravity is big G times the mass of Earth times the mass of the apple. And normally, if the apple tree is very tall, we'd have to divide it by the radius of Earth plus the height of the apple tree squared. But guys, if you compare 6 meters to 6 million, I think it's pretty safe to say that the 6 meter height of the apple tree doesn't really count, right? The apple is pretty much close to the surface of Earth. Notice, however, that the mass of the apple, which appears on both sides of the equation, almost by magic, the mass of the apple cancels out. And we get this tidy little formula for the acceleration of the apple. It's big G times the mass of the Earth divided by the radius of the Earth squared. Let's go ahead and let's punch in our numbers together. We get 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by the radius of Earth, 6.4 million meters squared. Bunch them up. Bunch them up, and then we can take a break. I'll take that answer anytime.
10 meters per second squared?
Nice. Laura, that's not random, is it?
That's a Newton or whatever, right?
Nope.
Oh,
what is that?
A joule?
No.
Shit.
We've seen.
I did something wrong.
What'd you say, Joel?
I did something wrong.
Okay, let's troubleshoot it. Are you using the Casio?
Yeah.
Watch me. Can you watch me?
Yeah.
7 EXP minus 11
Yeah.
times 6 EXP 24 divide by 6.4 EXP 6. Now, Joel, watch my moves here.
Oh, I didn't square it.
Square and then equals.
Yeah.
By the way, what just happened there was exactly what's supposed to happen. Joel's doing it right. If you don't get the answer that everyone else gets, you're not supposed to hide and pretend it didn't happen. You're supposed to say, hey, B, I didn't get that number, and then I will show you what to do and help you troubleshoot it. If you do not do that, you will not learn, and you will be getting it wrong on the test. That is worse. Joel will not be getting that one wrong on the test because he figured out what he did wrong. All right. What is this? We've seen this before.
The local acceleration of Earth's gravity.
That's right. This is little g. Who was the first person to discover the local acceleration of Earth's gravity?
Galileo.
So, Laura, did Newton waste his time doing this? Since it had already been discovered, was this a waste of time?
No, because science is about trying again. But
No, wait, there's more to it than that. It's
and
not.
also because it shows that those two formulas equal each other.
Well, this was started off as a demonstration of how you could use them together. But what we discovered is that there's a formula for little g on any planet. Guys, the moral of the story is that there are two types of physicists found in nature. There are scientists that are like Galileo, and they are called experimentalists. They build an inclined plane, and they investigate the truth of nature by rolling spheres down the inclined plane, by making observations and deducing the conclusions. Then there are scientists that are like Newton, which are theorists. You know, Newton didn't build an inclined plane like Galileo did. He didn't get any sawdust in his fingernails. He didn't get any splinters. He just sat around with a funny hat and a pen, thinking deep thoughts, okay? But he arrived at the same results that Galileo did using math in his mind. And in a way, there's something to be said for each of the techniques. Science requires experimentalists to actually go out and make sure that we didn't screw up at our math. We need someone with a pair of overalls and a grease wrench and who's going to go out and build an inclined plane or a particle accelerator and actually watch what happens to make sure we get it. But we also need people like Newton who can deduce, Galileo didn't know that the spheres fell because of gravity. Galileo knew that the mass of the falling object did not affect the acceleration, but he couldn't see why. Newton now knows that the gravitational acceleration is caused by big G, by the mass of the planet and the radius of the planet squared. And if you went to Mars, Newton could tell you what the acceleration would be on Mars, knowing its mass and its radius. Galileo could as well, but he'd have to build his inclined plane on Mars again and roll the spheres all over. So theory is nice if you don't screw up, but we also need to fact check it with experiments. Both are important. Also, as Laura pointed out, it's a nice demonstration of how you can combine the law of gravity with the laws of motion and rediscover truths about nature. And that's what we're going to do after tea break. We are going to see how Newton reinvestigated Kepler's laws, but understood them at a deeper level. And those are going to be helpful laws for us to investigate the cosmos and stars. So let's take like close to a half an hour, chill, eat a sandwich, drink some iced tea, whatever you got to do. Let's remember to start the recording when we get back. Hit record. I had my own too. Shay, that's pretty good, if you can hear me. I love it.
Well, I figured I'm forgetful as the next guy, so I better put something in play.
Yeah, no, that was great. Takes a village. I had a lovely sandwich and watched all the depressing news of the day. I'm feeling great.
I just took a walk down to my pond and saw 5 little goslings from the Canadian geese, but I also saw something. So I saw something horrific though. A damn snapping turtle came up and ate one of them.
What? You saw a snapping turtle eat a gosling?
Yeah, man, it stunk.
Shit. I didn't know a snapping turtle would take on a gosling. Evelyn's crying. Evelyn's actually missed it.
I know. I shouldn't have shared, but I was like, God damn it! Like what? Hey, buddy.
You should have got that on YouTube, man.
Circle of life.
A snapping turtle ate a gosling? Now,
yeah, just a little one. Probably. I mean, they can probably fit in the palm of your hand right now.
I know.
One of the pairs, and then another pair has it. They lose them every year.
I saved a baby gosling once. I found it in a rainstorm in a pond, and we built a little pen in our backyard and reintroduced it to its family. It was a feel-good story of the year.
Aw.
But from what I remember, Canadian geese are they're pretty aggressive when it comes to
They
defending
are.
their young. So I'm surprised that snapping turtle got away with it, because I'm guessing an adult mama goose could give that thing a peck or two that would make it rethink. But did the parents freak out, or did they just happen so fast?
Oh yeah. Oh yeah. The mother took the other 3 or 4 away immediately, and the father, they don't usually go like way down into the water, but he went right down into the water. He came up, he was all so
Holy shit! What an
That's
Must be a full moon.
Yeah, exactly. Tidal forces.
Hey, Brendan.
Yeah.
Were you unaware of something that was supposed to happen yesterday?
Yes. What did I miss?
SpaceX.
Oh, the shuttle launch.
Oh yeah.
My tutors reminded me about it. I was supposed to watch. Do you watch the launch?
Well, a friend of mine told me, and I'm like, hey, wait a minute, this is space. Why didn't Brendan say anything about it?
To be honest, my tutors had emailed me that day asking me if I wanted to watch it with them. And I said, I can't, because I'm going to be teaching until 4. Maybe I'll try to log in at that point. But I think prosecuting the day's class just made me forget. It's embarrassing to admit. But I had
on Saturday now.
Huh?
Yeah, because it
postponed it, right.
It was tornadoes and thunderstorms that were passing through. So it's going to be Saturday at like 3:22, I think.
Now remember what happened.
Like that.
I was going to try to watch it with them, and they told me it was postponed. And I said, oh, okay, well, then I'll just put this off until I'll wait for it. But yeah, so this is going to be the first time that SpaceX and NASA are collaborating to send humans back into space. The space shuttle program has been undergoing a revamp where in order to bring our next generation of space shuttles online, we've had to farm out the traveling of astronauts to the International Space Station to the Russians. And the Russians have been launching them in the Soyuz rockets over the Black Sea. So we've been sort of renting an Uber to the International Space Station for the last several years. And so this is a milestone.
For $8.9 million a trip.
Going to space ain't cheap. A lot of it's fuel. There's a lot of people that are involved in those missions, you know?
Yep.
The fact that we're sending our own astronauts back to space is a good sign, though. It means that we're slowly getting there. So, Joel, you said that was what, Saturday at 3:22?
Yeah, something like that.
So it's actually kind of awesome that you brought that up, Joel. I'm so grateful you did, because in the second part of today's class, we're going to calculate the escape velocity from Earth, which is what the shuttles have to achieve. And for our lab, we're going to calculate the period of the ISS. So that'll actually be a nice dovetail with these lectures. If you're home around 3:22, you might go onto the NASA website and watch the launch, and I'll try to do that too. And that would be a pretty nice thing. So that'll kind of tie in. Joel, I should have brought that up. You are right. And I'm very glad that you did, because it's deeply related to our class today. All right. So to get down to it, we have two more little problems to do before we get to our lab. And I'm going to sort of introduce them here by introducing a set of formulas known as Newton's version of Kepler's 3 laws. So let's do that together up on the board. It's also a nice chance for us to review Kepler's laws. All right. So title this little section of your notes, Newton's version of Kepler's laws. And what we are going to do is we're going to review Kepler's laws, and then we're going to see how Newton modified them by including the effects of gravity. An important piece of background that you may not understand before we go into this is that although Johannes Kepler devised his laws explaining how planets orbit the sun, Kepler was doing this before the concept of the force of gravity had been invented. Now, Aristotle had referred to gravitas as the natural desire for objects like rocks to fall towards Earth. So the concept of gravitas had been around since Aristotle. But no one had kind of codified the concept of, oh, there's a force between masses, and that's what makes planet orbits. In fact, Aristotle believed that gravitas did not work in space, and that gravitas was only restricted to planet Earth. It was Newton who connected the gravitas of Earth with the gravity of outer space and realized that this is what is causing the orbits of the planets. Once he did that, he was able to modify Kepler's laws in such a way that they became more generalized and could describe any kind of binary orbits. So let's do a little review. Class, what was Kepler's first law, and what did that state? We're going to do Newton's version of Kepler's first law. But what was the law called? Let's review our notes.
Law of ellipses.
Yeah. And the law of ellipses, if we, let's get our slideshow up here. The law of ellipses stated that a planet orbits the sun on an ellipse with the sun located at a focus point.
Hey, sweetie. Okay, I got you.
So this is Kepler's version, slide 58. Notice that the planet is on the ellipse. This is what we did in our lab on Tuesday. And the sun is offset and located at a focus point. Newton saw that this was a pretty good approximation of things when you had a big fat star and a little wimpy planet. But Newton now realized that it was possible to have binary stars, two stars of equal mass, which could orbit each other. And that led to a conundrum. What happens if you have two stars, M1 and M2, and what if the two stars are equal in mass? Who would go on the ellipse and who would be located at the focus point? One option is that M1 orbits M2 on an ellipse with M2 at the focus point. Another option is that M2 orbits M1 on an ellipse with M1 at a focus point. But if they're equal masses, how do you decide who gets to go on the ellipse and who gets to be at the focus point? Want to take a guess at what happens? How would orbits work?
Can you repeat the question?
If I had two stars that were equal to each other in mass, and they were going to go into an orbit around each other, which star would be on the ellipse and which star would be at the focus point?
Both.
Okay, so explain that to me, Evelyn. What do you mean by both? They're both on ellipses?
They would both be like in each other's orbit.
Okay, will they both be on ellipses?
Yes.
Okay, what will be at the focus point?
The center of gravity.
Exactly. But the center of gravity was a concept that Newton had to develop to answer this question. We also refer to the center of gravity as the center of mass. And let me give you a cartoon walkthrough at how the center of mass works. It's actually, it looks pretty evil when you write out the equation, but the concept is very simple. If I have two stars and the two stars are equal in mass, the center of mass is exactly in the middle. If star 1 is 4 times more massive than star 2, the center of mass will be shifted to 1/4 the distance from star 1. If star 1 is instead 10 times greater, the center of mass will be shifted to about 1/10. the distance between the two stars. You see? So the center of mass is a center that is weighted by the ratio of their masses. In the case of something like the sun and Earth, the sun is literally 1,000,000 times more massive than Earth. And because of that, the center of mass of the Earth-Sun system is 1/1,000,000th of the distance between the Earth and the sun. Now, I remember that 1 AU is 150 million kilometers, right? So
Yes.
what would a millionth of 1 AU be in kilometers? What do you get if you divide 150 million by a million?
150
Say that?
150?
150 what?
kilometers.
Right, but here's the problem. The sun has a radius, if you remember, of 700,000 kilometers. And that means the center of mass of the Earth-Sun system is a point somewhere inside the belly of the sun. In other words, Earth does not orbit the sun on an ellipse with the sun located at a focus point. That's simply not true. Earth orbits a point inside the belly of the sun on an ellipse with a point inside the belly of the sun at a focus point. Oh, and by the way, the sun also orbits a point inside the belly of the sun on an ellipse with a point inside the belly of the sun at a focus point. Or in other words, the sun wobbles on its axis due to gravitational tugs from the other planets. Most of the sun's wobble is caused by Jupiter. They call this stellar wobble, by the way. It's kind of a thing. Most of the wobble is caused by Jupiter. The secondary wobble is a combination of Earth and Saturn. Earth is 1/100th of Saturn's mass, but Saturn is 10 times farther away. So if you do the inverse square law, that's 1/100th the force. So Saturn and Earth tug on the sun with the same, roughly the same effect. All the other planets have a tertiary effect. So actually, the sun is actually doing a more complex rosette wobble from all these other planets. But this is what it would look like in an idealized case in which the star and the planet had perfectly circular orbits, and it was just one star and one planet. This is what stellar wobble looks like. This is the essence of how Newton re-derived Kepler's first law and made it more interesting and more general. Class, in this cartoon example that you see, both planet and star have perfectly circular orbits with 0 eccentricity. I wonder what it would look like if their orbits were not 0, if their orbits were eccentric instead of circular. Do I have a picture of that? No, but I have a picture of it in my star lecture, and I'm going to show it to you. Get out of here. This is a later slideshow, but I want to. Slide 94. This is what it looks like, Evelyn, if two stars of equal mass orbit a common center of mass. Notice that star 1 is orbiting the center of mass with the center of mass at the second focus point. Star 2 is orbiting the center of mass with the center of mass at their F1 focus point. But they oscillate around each other in this complex B dance in which the center of mass is always kept in between them. In a sense, this is what every star and planet are doing. It's just that the orbits of planets tend to become circularized over time due to gravitational nudges from their friends. Cool. How do we, oh, there's one other aspect to Kepler's first law. Kepler only believed that ellipses were possible orbits. Newton was able to derive that not only can orbits be elliptical, but they can be one of a class of sections that we call conic sections. I believe even Kepler knew something about conic sections, but Newton really drove the point home. The idea goes like this. In slide 62, how many ways can you slice a cone? Well, you can slice a cone perfectly horizontally, and that creates a circle. You can slice a cone at a diagonal, and that creates a squash circle called an ellipse. If you slice a cone through the bottom, you get a sort of U shape called a parabola. And if you slice the cone perfectly vertical, you get a slightly different geometry that's called a hyperbola. Circles, ellipses, parabolas, and hyperbolas are geometrical shapes that we refer to as conic sections. And it turns out that all gravitational orbits always obey one of these types of conic sections. That means not only are there bound orbits, circles and ellipses are where the planet is bound to the star, but it's also possible to have unbound orbits, where a comet or a distant star can slingshot off of your gravity and then get flung back out into space. We call this a gravitational slingshot. Almost all satellites that we send to the outer solar system usually perform a gravitational slingshot off of Jupiter or Mars to build up speed before they get out there. Kepler only conceived of bound orbits. Newton could see that gravity was capable of creating unbound orbits as well. And there are certain comets from the outer solar system that pass by the sun once and get flung out into deep space and never return. So we see this kind of thing happening. Let's take it down as a note. Two masses orbit each other on conic sections with the center of mass at a focus point. Okay, class. What was Kepler's second law?
Law of areas.
And how did that go?
A planet sweeps out equal units of area in equal intervals of time.
Right. Let's look at the cartoon for this. So in Kepler's second law, we have a planet sweeping out equal units of area in equal units of time. And when Newton derived this himself, well, let me move my moon and my Earth here. Newton discovered that unlike the first law, which required modification, that Kepler's second law of equal areas was just simply true. It required no modification. It was perfect. A planet or a binary planet, whatever it is, truly does sweep out equal units of area in equal units of time. However, Kepler was able to derive a little bit deeper into the equation and realize that this is being caused by an effect in physics known as the conservation of angular momentum. Now, I'm going to take notes on that in a second, but let's review some basic concepts from a physics class that you may never have had before. In physics, we often introduce a couple of concepts, and in a mechanics course, one of the key concepts we learn about is called momentum. There are two variations of momentum. Linear momentum is usually your first introduction, and then you get into the more useful angular momentum. let's just kind of talk our way through this for a second. For some reason in physics, momentum gets the letter P, probably because we've used M too many times. And we use P to represent the momentum in physics. It's the product of an object's mass times a velocity. And usually you have something like a bullet or maybe a pool ball. It's got a mass and it's traveling at some speed. And momentum causes the first ball to come to rest and the second ball to move when they strike each other. Momentum is a conserved quantity in nature. The total momentum of a system must be completely conserved. And that gives you Nostradamus-like powers. Momentum might be more complicated to think about than velocity, but if you think in terms of momentum, you get predictive powers that you don't have when you think in terms of velocity. For instance, during collisions, if the two objects are of equal mass, usually the first object will completely come to rest and its velocity will be 100% transferred to the other object. There are two other variations on this as well. One variation is equal masses. Like you've all played a game of pool before, presumably. You know that the cue ball will basically come to rest and the 8-ball will keep moving. In the case where one of your particles is really small, like my rubber ball, and the other is big, like this crazy throw-up ball, when the little particle strikes the big one, its momentum gets ricocheted back and it bounces off. The third case is where you have a big fat bowling ball striking a BB. If a bowling ball strikes a BB, it kind of snowplows it and picks it up and they move together. So there are three different regimes for collisions. When they're equal, momentum is transferred from one particle to the other. If they're really lopsided, either you scoop up the small BB or the BB bounces off of the bowling ball. But linear momentum is something that's kind of intuitive. You get a sense of this if you've ever had to, I don't know, push, what's a heavy thing that we have to push sometimes? A shopping cart full of groceries. I don't know. Okay. The thing in physics is that anytime you have a quantity like momentum, it tends to have an evil brother, an evil twin brother that's caused by taking something into rotation. Rotation makes things more complicated. So there's a comparison or an analog to linear momentum called angular momentum. Angular momentum is, here's the setup. You've got a particle on a string and it's being whipped around in a circle, kind of like that Ewok thing in Return of the Jedi. Okay, you're whipping the little pebble around on a string, and your object has a mass and a velocity, and it has a radius of orbit that's sometimes called your moment arm. Angular momentum, which we use the letter L for, is the product of mass times velocity times the radius of orbit, or the moment arm. And angular momentum is also a conserved quantity, but it's way weirder than linear momentum. The first thing about angular momentum is that the direction of angular momentum is considered to be along the axis of rotation. And angular momentum can sometimes work in mysterious ways, as the following demo will attempt to show. This is, of course, a lot more impressive in real life, but here I have myself a bicycle wheel, right? I'd like to get a little distance between me and the, hold on. So I want to get my angle wide enough for you guys to see what's going on. Here's my bicycle wheel. And it's just a normal bicycle wheel, no tricks or props here. It's got a string attached to the end of it, so that if I hold up the bicycle wheel with the string in one hand, the bicycle wheel just kind of flops over like this, okay? So you can see it just kind of wants to flop over. Now, if I give this bicycle wheel some angular momentum, the angular momentum points along the axis of rotation. And some very interesting things happen. If I spin this up, I can hold it by the string, and gravity is unable to tilt over the bicycle wheel. It undergoes a motion called precession. Watch, even if I whack on it, ready? Actually, I should be doing this. I should be putting this on the main screen, not on the share screen. So this way I can see what I'm doing. So here's my bicycle wheel. Woo! The angular momentum on this is really weird. I can hold it up by the string, and gravity is unable to pull the bicycle wheel over. Instead, it goes through something called precession. Watch this. I can't knock it over. This is why you don't fall over on your bicycle when you're in motion. The conservation of angular momentum is real buggy. It wants to do buggy things. I wish I had a little spinny stool here. Oh, wait. Can I make this even better? Let's see if I can make myself turn. Okay, this is where the professor falls and breaks his goddamn face, and you guys get to laugh, okay? All right, let's see how this works. Oh, shit, I'm asking for it now. All right. Hold this. Let's see if I can get myself. I think what you have to do is you have to twist it. Whoa! I can rotate myself. Oh, shit. All right, I just smashed one of my lamps. Did you see how I twisted? You couldn't see what's going, but I just bent it up like this. And to conserve angular momentum, my body started to turn. That was pretty fucking crazy. All right. Obviously, you know, the frame is kind of limited here. I got to figure this out in the future. Angular momentum is weird.
But kind of like how a helicopter works.
Huh?
Like a helicopter works.
Yeah, absolutely. Helicopters, planets going around the sun. In the case of a planet going around the sun, which is a little more in my comfort zone than helicopters, although I imagine steering and turning helicopters probably has its own kooky logic because of that. In the case of a planet and the sun, when the planet comes in towards perihelion, its radius of orbit is shrinking. In order to conserve angular momentum, the particle has to speed up and go faster so that angular momentum is conserved. This is why one of the reasons why it's very, very difficult for two planets or two stars to actually collide in physics. Unless they are pointed dead nuts at each other, even a slight discrepancy will cause the conservation of angular momentum to make them kind of slingshot off of one another. It's very, very difficult to manufacture collisions in space. It's just very tricky. There's so much room to miss your target, and there's so little target to hit. Let's try to consolidate what we just learned into a simple note that we can digest. The law of equal areas is true, but there is a cause. The cause is known as the conservation of angular momentum. And angular momentum is a mass times a velocity times a radius of orbit. By the way, I've got some WD-40 in my toolbox. I should really grease up these stools and see if I can do that experiment again and really whip myself around. That'd be kind of fun. Joel's like, that sounds like the beginning of a broken arm story.
I'll have 911 on speed dial.
You and Shay will have a similar experience in life.
Yeah, exactly. Forget having the apple dropped on my head. I want my head dropped on the apple.
Yeah.
Okay. And now it's time for the big kahuna, what we've been building up towards all class. Newton's version of Kepler's third law is its own kind of madness. We've been doing all of this. All of this has been an excuse for us to lead up to this formula. The formula is known as Newton's version of Kepler's third law. Henceforth, Newton's version of Kepler's third law will be known to us as NK3, because that's a lot easier to say. There are two versions. The first version, which is the classic version, is the one that we tested out in our homework today. 4 times pi squared times a cubed divided by g times the sum of two masses. That's the first version. It works for any two orbital masses, where the distance will be measured in meters, masses will be measured in kilograms, and the period will be measured in seconds. There's a second version of this, which is algebraically solved for mass. That's where you take the two masses, you flip them up to the top here, you take the p squared, and you flip it down there. This version is called NK3 solved for mass. The total mass of my system is 4 times pi squared times a cubed divided by big G times p squared. It is the second version that is the most important to us in this class. This formula is the formula that all astronomers need to use when they measure the masses of stars and planets. Think about it, kids. You can't tiptoe out to Jupiter and give it a dunk on the Stop and Shop scale. The only way to measure masses is by studying the orbit of moons around some large object. Sometimes astronomers refer to this formula because of its usefulness as the cosmic balance beam. Because balance beams are used to measure masses, not Stop and Shop scales. The cosmic balance beam. This formula means a lot to us in this class. I'm going to make you use it practically every week for the rest of the semester. Because of that, you had several homework problems on it. The third homework problem, we tried it twice. Remember that? We calculated the mass, the period of a planet going around a sun, and then the period of a planet going around a sun 4 times as massive. We also used it to find the combined mass of Pluto and Charon. We're also going to use it in our labs today. Let's see how we're doing on time. I'm losing track of things. Oh my gosh, it's 2:49. Okay. Instead of doing a sample problem, because I knew that I would need more time than I had to work with you, the sample problem we are going to try as part of a group lab together, okay? For now, I want to introduce one more formula. I'm going to do it kind of ugly and awkwardly, but I have no choice. With my last few moments, I want to teach you one last formula. Let me see all your faces, because I'm about to erase. I want to see if anyone's still note-taking here. Everyone looks good. Okay. The last thing that we can do with Newton's laws of gravitation is we can calculate something called the escape velocity. And I'm going to just give you the quick and dirty version because that's sort of all we have time for. Let's start here. The escape velocity is defined as that speed that any object, let's say that fixed speed, because it's fixed for a particular planet, that fixed speed any object needs to escape a planet of radius r and mass m. Famously, the escape velocity does not depend upon the speed of the rocket. The symbol that I will use is v/ESC. That's the sort of standard escape velocity variable, of a velocity with an escape next to it. Let's draw the picture, then we'll draw the formula. The picture is of a planet. Here's your rocket that's attempting to blast off with some velocity. The planet has a radius r and a mass m. In our homeworks, we were supposed to do parts A and part C. I'm going to rearrange it, and I'm going to have us submit 2 different problems for homework. We're going to try one now. So, guys, let's include this as part of your homework number 3. What was the last number, Laura?
Number 58.
Number 50 what?
58.
And we were supposed to be A and C, right?
Yep.
I'm going to change it to 58A. I think they wanted us to do it for Mars, right?
Yes.
Okay.
Yes.
Instead of doing it for Mars, I'd like to go off-roading here. I want us to do it for Earth instead. So this is going to be one of the things that you photograph for me. Before you calculate the escape velocity of Mars, I think it's better to calculate the escape velocity of Earth. In a normal semester, I would have you calculate the escape velocity of Earth as a in-class problem, and then I would assign Mars and Jupiter as homework. But since we're a little bit compressed for time, I say we do the escape velocity for Earth and we turn that in for homework. Do you guys like that? I like that. Okay. Let's go ahead and do it. So, the mass of Earth is 6 times 10 to the 24 kilograms. The radius of Earth is 6,400 kilometers, but we need that in meters. Hey, Joel, what's 6,400 kilometers in meters?
6.4 times 10 to the 6th.
6.4 million meters. We'll let Joel do that in his head in the interest of time. The escape velocity from Earth, then, is the big old square root of 2 times big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of the Earth, 6 times 10 to the 24. Did I write down the escape velocity formula?
No.
I don't think I did I?
No.
I'm a moron. Okay. I apologize, class. Here's your formula. I'm sorry. The escape velocity formula is the square root of 2 times big G times the mass of the planet divided by the radius of the planet. I was trying to go so fast that I forgot to give you the formula. I'm so sorry. That was real dumb of me. All right. Anyways, back to the game here. 6 times 10 to the 24 kilograms divided by the radius in meters. Oh, let's put those notes into our notes. Masses are to be measured in kilograms. Radii in meters. What do you think the velocity is going to be in? What are MKS units of velocity?
Seconds?
Seconds is a unit of time.
Dang.
Wait, what'd you ask?
What are MKS units of velocity?
Meters per second per second.
That's acceleration.
Oh,
I want
meters
velocity.
per second.
That's right. Okay, good. Y'all with me? Divided by 6.4 million meters. Okay, punch them up. Punch them up. Jose, you want to give us an answer? Catherine's hiding from me, so you're next on my list. Oh, by the way, Jose, punch all the stuff in and hit equals and then square root after you hit equals, okay?
Brandon, is that how the P-Calc works? Do the square root at the end?
No, for P-Calc, you should do the square root.
At the beginning? Okay.
Wait, are we talking Pan-Ecal or P-Calc? For Pan-Ecal, I would hit the square root first, open parentheses, 2 times 7, oh fuck, 7 exp minus 11 times 6 exp 24 divided by 6.4 exp 6, close parentheses. That's how I type it in, come on, in P-Calc. Because P-Calc is a line entry calculator, so you might as well have the square root out front.
Copy.
What do you guys get?
Brendan, did you say equals first or square first?
It depends what calculator you're using. I believe you're using the Casio, correct, Jose?
Yes.
Then you hit equals first, and then you square root.
Okay.
What do you get?
4.3 times 10 to the 15th.
You forgot to square root it.
I did. After the... Wait.
I don't know what you did. Hey, Jose, you want to do it with me?
Mm-hmm.
Let's do it together, okay? 2 times 7 exp negative 11. So far, so good?
Yep.
Times 6 exp 24. Divide by 6.4 exp6 equals shift square root.
You press shift first, right? Yep,
Yeah, because the square root's in the upper menu. It's the orange key.
Okay. Yeah, I got that wrong the last time. So I got that.
So what do you have now for your answer? Rounded to 2 sig figs. No scientific notation required. Is your answer bigger or smaller than 1 million?
Smaller.
You don't need scientific notation then.
I got 11,456.
Let's round it even harder than that.
11,457 or?
No. Hey, Jose, when I say round to 2 sig figs, what that means is the first number is good and the second number is good and the rest of it is all bullshit. So how do we round? So how do we round it to?
So just keep it as 11?
Well, not 11. I didn't tell you to molest the number. 11,000 is not 11, Jose, right?
Yeah.
11,000.
11,000. Yeah. Yeah.
The magnitude is the same, but you're rounding it to 2 sig figs. What are the units?
11,000 meters.
That's length. I'm looking for velocity. Use your cheat sheet.
The meters per second.
Very good.
Velocity. Okay.
Hey, Joel,
Yes.
how many kilometers per second is that?
1.
Nope.
No, 11.
11. 11 clicks per second. That's the escape
Hey, I think
velocity. Is that fast?
No.
Yes. That's like 25,000 miles per hour. 11 kilometers in 1 second.
Oh, yeah, okay.
All right. Do you see that, class? That's your entire 58 homework, okay? You photo that and you turn it in place of 58. This, forget about A and C. This is the new problem 58. Can you guys do that for me when you turn in your homework? Otherwise, you don't want to do another one, do you? No, okay, we're good. We're good there, right? Yeah. Jump in Jehovah. Okay. I know today's a lot, guys. I knew today was going to suck before today even happened. But this is part of the growing pains of learning to punch stuff into your... Most of it is just calculator frustration, honestly. In fact, we got to get through that so I can start getting back to concepts. Today's lab is going to be a 2-for-1. We're going to do a problem and we're going to submit it as homework and lab. We'll double dip, okay? I think that's what we have to do. Actually, let's just keep it simple. The problem that we do today, you will submit as lab. And for the homework, you will do, what was it? What was the fourth problem, Laura?
57E we didn't do.
We're not going to do that, and we're not going to do F either. So, okay, let me diagram on the board what's going to happen, because I can understand if people are starting to get confused. Can I erase this, or is anyone still copying? All right. Okay. Today's homework number 3, is going to include chapter 4. Oh shit, I'm out of focus here. What was the damn problems again? Oh God. Does anyone have the numbers, please?
Yeah, do you want to start at the beginning or?
Yes.
Chapter 4, number 45, 47, 56, 57, D,
Okay,
E,
fine. So 57, D,
E, and F.
No, E and F
Okay.
are gone.
Gotcha.
And 58 was modified for the Earth. That's today's homework assignment. Does that make sense?
Copy.
That way we're done. Today's lab is on Newton's versions of Kepler's third law, and we're going to do 57E for that. Sound like a plan? Because these homeworks are really long and hard when you're doing them the first time. And the fact that we're not all in the same room together, it just increases the amount of bullshit we have to deal with, okay? Does everyone understand the plan and understand what they're going to be submitting to me? Because I wanted to avoid confusion. Okay, Catherine understands me. I hope the rest of you do as well. Yeah, some thumbs up. Okay, good. I got some head nods. All right. With that in mind, let us transition to our lab room. Let's take a walk to lab room. Oh, here we are. Today's lab does not require a handout or anything special. You just need some paper, okay?
So Brendan, with the launch that was supposed to happen yesterday, the reason they couldn't do it kind of relates to this lab, which is they had only like a 10-minute window in order for the rocket to go off and then meet the International Space Station as it was going.
Oh my gosh. So there was too many clouds or too many turbulent skies for them to hit
Yeah. Right. So it had to be like all the timing had to be perfect.
Right.
Which I think relates to this, right?
Yeah, well, we're going to calculate the period of ISS, and we'll discover that it goes around the world in like an hour and a half. That's the thing that we're trying to derive here. So it makes perfect sense to me that they'd only have like a short several-minute window to kind of team up with it. Probably the other constraints are fuel, right? Because one of the things that I didn't get to explain to you guys, I was going to explain it, and I decided not to overwhelm y'all, is that oftentimes when you watch a shuttle launch, and if you don't mind me giving this spiel again, a shuttle launch. If you guys can see my screen, there's a picture I really love of a shuttle launch seen from an F-15 fighter jet, or maybe it's an F-22, I don't know. Or here's one. Hold on a second. There's this beautiful picture that I really love to show students. It's usually one of the top hits on Google. I did save it, but I think it'll take me less time to find it here. I have to remember that the internet's always evolving, and I need to capture these pictures. Was it an F-22 or was it an F-15 fighter jet? Yeah. Look at this beautiful picture here.
Whoa.
Yeah, it's super cool. You can see this, I don't know if it's an F-15 or what it is, and they're photographing the shuttle launch. And can you see how it's kind of curving to the left, off and to the left there? It turns out that all you need to do is get your rocket up to 11 kilometers per second to get it into space. But because these shuttles are basically just a huge amount of fuel, someone was telling me about this clear see-through breakaway of a rocket where it's just mostly fuel and then a tiny little capsule. The limit of our current rocket technology, we can accelerate rockets up to just about 10 kilometers per second. So you would think that we wouldn't be able to get off of Earth and achieve escape velocity. But it turns out that if you're standing on a rotating Earth, Earth's rotation means that you have a velocity through space. And the further down in latitude you go towards the equator, the faster and faster your velocity is. So if you're on the North Pole, you just kind of spin around in 24 hours. But if you're on the equator, you travel a full Earth's circumference in 24 hours. And that gives you a velocity that's a little bit over 1 kilometer per second. The name of the game is to get your shuttle as far south as possible, like Cape Canaveral, Florida, where the speed of Earth's rotation is carrying you at 1 kilometer per second. And then what you do is you fire the rocket up at 10 kilometers per second, and you fire it into the direction of Earth's rotation. And Earth's rotation gives you that extra kilometer per second you need to get to outer space. So it's a pretty tight window. First of all, you're using the rotation of Earth to get there. But I could imagine, Laura, that if you're trying to hit the ISS as it flies by, you're getting rid of your booster stages and you're running out of fuel. As you've used so much fuel to get up to 10 kilometers per second, you're dropping all those booster stages and you have very little fuel left to actually target and hit the ISS. So if you miss it by more than 10, 15 minutes, you don't have enough fuel to catch up to the thing. And that's probably why it's such a narrow window. So if there's a few clouds in the sky or a bit of turbulent air and you're worried about losing your payload or your astronauts, you just postpone it until it's a clearer day with less unknown variables, right?
Yeah, that makes
I'm
sense.
old enough to remember the shuttle Challenger disaster, and that was like a traumatic experience for the entire nation. It kind of set the space program back a bit. I was a kid, and I think it was in second grade when that happened, and the teachers were all excited. They pulled out the TVs. We were all going to watch the shuttle launch, and we came back from recess, and they were crying and saying the shuttle blew up. Oh my God, it was horrific. So some of you younger whippersnappers don't remember that, but that makes sense to me that they would have this very tight window. It's mostly a fuel issue, probably. If you had extra fuel, you could pish posh around up there and try to hit your target, but you've used so much of your fuel getting up to 10 kilometers per second. There's not much left. You can do a few maneuvers, but not many.
Right.
Okay, today's lab exercise is going to be very similar to what problem 57E was. We're going to calculate the period of the International Space Station. It won't take too long, but it's another chance for you guys to do some maths. Now, I'm going to tell you that normally I use a lab on this because, as you can see from our class today, there's so much bullshit just trying to get everyone's calculator issues in line that I usually give each of you some one-on-one attention, and I walk around to each station and make sure each person is punching the right buttons. I don't exactly know how I'm going to recreate that magic on air here, but I will try. Let's see if I can share my phone screen so you guys can follow along on my paper. Let's see if this works. Share screen, iPhone. Okay, we got that. Let me go into my settings real quick. And let me deactivate the screen lock. Oh, auto lock, never, it's already there. All right. I've got some very nice paper here. Some gridded paper. It's always nice to have a nice piece of paper. These things. I got some maths on there. Okay. So let me get a sharpened pencil here. Take that one of my fresh Dixon Ticonderogas. And let's start by putting our name up at the top. We will put Astronomy 1020. That's our section. And this is lab number 3, I believe, right?
I think number 4.
Title it. Oh.
Right?
Yeah.
It's 4. Yep.
Wow, time is flying. I'm sorry. Thanks, guys. Lab 4, period of the ISS. That's what we can call this, the period of the ISS. All right? Okay, so the question that we're going to try to do is we're going to use NK3 to find the period of the International Space Station. And let's try to draw a picture of this. Let me know if you guys have trouble reading my handwriting. I'm actually going to make a beautiful picture using a compass because I'm kind of in the mood to do some fun art here. I'm gonna make a nice, you know, not too big, but big enough Earth. Something looks like so. You guys might want to use a coffee lid or the back of a mug. A mug might make a pretty good sized Earth circle. This is about mug sized. Do you have a coffee cup around? A glass, whatever. Make a nice circle. Do it right. I'm going to mark the midpoint. And I'm going to draw in the radius of Earth with a straight edge. Okay. Here's how I like to draw my rocket. I'm going to have my International Space Station. I usually make it like a box, okay? And I put some sort of solar panels on the edge of it. So, you know, something like this. Kind of looks like a piece of candy or something. And here's the info that I'm going to be working with here. Oops, sorry. Okay, so the radius of Earth is 6,400 kilometers. The mass of Earth is 6 times 10 to the 24 kilometers. Oh, kilometers. What the shit am I doing here? Kilograms. Now, the height of the ISS, I believe, is about 400 kilometers above the surface of Earth. That makes it a little bit taller than your typical apple tree, right?
Yeah, a little bit.
A little bit. The mass of the ISS is 400,000 kilograms. It's 4,000 metric tons. And a metric ton is 1,000 kilograms. So let's get all that framed for you so you can copy all that info. Just take a second to catch up to me there. Everyone feeling pretty good? I don't want to go too fast and burn you guys. All right. All right. Let's start by writing our equation down. The period, if we just put the square root on the other side, the period is the square root of 4 times pi squared times a cubed over big G times the two masses, which are the mass of Earth plus the mass of the ISS. We know 4 and we know pi. Those are buttons on our calculator. Let's now focus on the A. Class, what is the A in this case?
$6,800 kilometers.
Very good, Joel. The A, this is a trick, you got to know to do this, is the combination of the height of the rate, because it's orbiting the center of Earth, right? It's the height plus the radius of Earth. So A is the radius of Earth plus the height. And Joel correctly points out that 6,800 kilometers. Let's convert that to meters now, because we have to have A in meters.
Shay?
Shay?
Oh,
We-
boy.
We call good idea, Joel. Let's have Shay do this. Okay, Shay, I did step 1 for you. What's step 2?
What, Let me just finish writing this down. One sec.
Sure. Take a moment.
You go fast.
I do. Well, I try to pause so that I understand.
No, I know. I know. I'm just kidding.
And half the time you can't see what I'm writing until I move away from it. So.
Okay, so what's the question?
We're looking to convert, because this is an MKS formula.
Right.
Kilometers are not MKS. We have to convert them to meters.
The meters. Okay. So 1,000 meters equals 1 kilometer. So we're going to add 3.
Hold on, wait. Units first, numbers second.
Oh, sorry. Kilometers on the bottom.
Yep.
Meters on top.
Yep.
1,000 meters.
Yep.
To 1 kilometer.
Good. And then what does that turn out to be?
That turns out to be.
Oh, hold on, I'm upside down here.
60.
Let's do 6.8.
Okay, 6.8 times 10 to the 1, 2, 3, 4, 5, 6, right?
Very good. Because it's 1, 2, 3, 4, 5, 6 places that we moved the decimal point.
Right.
Right. Now I want to deal with this quantity here. This quantity here is known as the total mass, m tot. And I want to evaluate m total by itself first. Mass of Earth plus the mass of the ISS, which equals 6 times 10 to the 24 kilograms plus 400,000 kilograms. Let's add them up. Will, I'd like you to punch those in for me if you could. Can you see that? Okay?
6 times 10 to the 24. Wait, what? Hold on a sec.
Can you add those two?
Yeah, let's see. 6 exp 24 plus 100,000. What the heck?
What'd you get?
I keep getting 6 to the 24.
Me too.
No, that's the mass of Earth. I want you to add the mass of the ISS to it.
Me too. I get
Yeah,
the same thing. That's weird.
No, guys, you don't get it. I don't want just the mass of Earth. I want you to add the mass of the ISS.
So small that it's like insignificant.
Ah, damn it, Evelyn. Who said that? Was that Sarah? Was that Evelyn? Why are you spoiling my fun? I was playing a joke on those guys.
You jerk.
Because
this is so much smaller than that you can totally neglect. You got to know when to play this trick, though. And if you didn't think to do it, you wouldn't think to do it. The mass of the ISS is so small. You know what's happening here? Will, this is a 6 followed by 24 zeros. You know, like Bill Gates probably has like $50 billion. And suppose Bill Gates drops a penny. Do you know what $50 billion plus a penny is?
Who cares?
Exactly, it's $50 billion. And this is even more extreme than that, because billion is 10 to the 9. This is 10 to the 24, right?
Right.
This is less than adding a penny to Bill Gates's piggy bank. Okay, so what we're going to do is we're going to basically say that the total mass of the system is approximately or damn close to just the mass of Earth. And that's what we're going to plug in, all right? So let's go ahead and set this up. So we have p squared. I'm sorry, we're not going to do p squared. we're going to do P is equal to the square root of lined paper is really nice because it kind of has the bars built in right there for you. 4 times pi squared times open parentheses, it was 6.8 million meters. And that's cubed. Okay. Here, let me see if, I think horizontal mode might be a little nicer here for you guys. Okay. And that's divided by big G, 7 times 10 to the minus 11. The units are meters cubed per kilogram per second squared, times the mass of Earth. Six times 10 to the 24 kilograms. That's the whole thing right there. Once you're done writing it, we got to try the punching of it. Do you want to see me do it? I'm kind of quick here. So here's me doing it. 4 times pi squared times 6.8 exp6 shift cube divided by 7 exp minus 11 divided by 6 exp24 equals shift square root. Okay, I'm a little bit quick. Let's try it slower. Cassiopeia, all right, let me just take a survey here. Actually, I got a better idea. Why doesn't each and every person show me their screen and I'll tell you if it's right or wrong, and then I'll focus on the people who got it wrong. Laura has it right. Shay has it wrong. Shay, we're gonna have to work with you. Shay, which calculator are you using again? You're muted, Shay. Shay, you're mute.
Shit, I'm an idiot.
That's all right.
I just quickly was using my my iPhone thing, but I'll get right on to pCalc and do it.
Very good, Catherine. You got it right. Evelyn, Jose, Will, I want to see you all. Who else is out there?
Can I see the problem?
Yeah. Oh, wait, hold on.
Oh, what if I plug that in? Right?
Damn it. Jose, that didn't come out right. Will, doesn't look right. Okay, let's focus on Jose and Will. Jose and Will, you both have my calculator, so can you punch with me?
Yeah.
All right, so I'll go slow this time. 4 times pi squared times 6.8 exp6 shift, and this is cube right here, divide by 7 exp negative key 11. Here comes the key moment. Divide by 6 exp 24. Now equals, and now shift square root.
Yeah, so I got that. Yeah, so what I did wrong was I put multiply instead of divide for the.
That's why I said that's the key step. It's really tempting to put multiply there, but your
Yeah.
calculator needs to know that you wanted that in the bottom, so you actually have to hit divide there. That's a trick, okay? That's the key trick, Jose, and you just learned it. Okay.
Yeah, that's what got me.
Huh? Yeah, it looked like that got you too well. Yeah, that's classic.
Yeah.
So right now I want to focus on Shay and I want to focus on well, Joel and Sarah. I haven't seen Joel. What do you have? Did you get it? All right, Joel's got it. Sarah, can you show me
On the
what you
second time around. I don't know what I did wrong the first time.
I'm sorry, say that. Who was talking to me there?
Just one second.
I can only see about 6 of you at a time, so I'm scrolling back and forth. Shay and Sarah, are you having trouble getting it?
Yeah, the problem with this pcalc thing, I can't find like where like the cube is, and I don't know how to do that.
How about you, Sarah? Same troubles?
What was the answer?
Well, 5,400. What'd you get?
Not that.
All right, well then we got to go through it by the numbers. Let me get my iPad, hold on.
Sorry.
Wait.
Let's see what I have in this bloody thing. You said you were using pcalc, but Sarah,
Yep.
what are you using, Sarah?
PannyCal.
Okay, geez.
Oh, wait a second. Maybe I have let me check. Oh, it's PannyCal. I'm sorry.
It's fine. Hold on. I gotta just. Where's my app machine here?
I thought I downloaded pcalc. I didn't even realize it was just PannyCal.
PannyCal kind of sucks, but whatever. Hold on. I just search. There's probably a better one than this.
No, we'll all have our Casios on Tuesday.
Thank fucking God, because I can't take my.
I know.
It just makes everything 17 times more difficult, you know?
Yeah, I know. Total loser.
No. Look, it's okay. I just don't think you guys understood the urgency of the problem.
The gravity of the situation. No
Yeah,
problem.
you didn't understand the gravity of the situation. That's because you hadn't had your law of gravity yet, but now you do. Get. Oh, wait a minute. I don't need to download it because I can just show you my screen, right? So I'm talking now to, where are you?
For PannyCal?
Yeah, okay, Shay and Sarah, you're in my thing. So ready, let's do this here. PannyCal. Okay, you guys watching my screen?
Uh-huh.
Clear it out. Well, there's a delay here, there's a lag. All right. Whoop, lag.
There it was.
Okay, so we're gonna do the square root first. So hit the square root. Are you with me, Sarah?
Yep.
4 times pi times 6.8 exp6
You forgot to square.
Oh, shit.
Damn it.
Who's teaching this class, Evelyn, huh? All right, so thank you. Please keep me on track. Times 6.8 exp6, all right, to the power of x to the y 3, divide by 7 exp minus key 11. I hate how they have the minus key there. Divided by 6 exp 24 close parentheses equals.
I was multiplying there. That was my issue.
Oh, yep. Everyone does that. Shay, did you get that?
I'm still working on it. One sec.
We got plenty of time. Oh, my back hurts from hunching over this fucking computer. Okay, here we go. Shay, talk to me.
Huh. I did everything you did and I have, oh no, I didn't.
Can you show me the screen, please?
Sure.
Hold on. Closer. Closer. Closer.
Turn it, Shay.
Close it. Close it. Oh, I can't read that.
Wait, let me turn off this light. Wait a second, man, that's what it is.
I'm afraid to close out my phone because all right, Shay. Hold on.
Shay, try rotating it to the right.
Shay,
okay.
Just do it again. Just like you did. I finally full screened you. Just do it one more time. One more time.
It doesn't rotate. It sucks.
That's okay. Just hold it up and leave it there for a second so it focuses. I got to get your closer. 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 You're glared out. Oh, here we go. Hold on. Oh, dude, you used EXP for pi. You also have 6.8 to the power of 63. Oh, fuck, Shay. Okay, look.
What a loser.
All right, hold on. Okay. Here, no, wait, Shay, we're gonna do this the right way.
Okay. It's just
all
that
Greek to Shay.
When you type it in, I can't see which like one you're tapping and I get like confused which button it is.
Hold
Sorry.
on. Can you see this? Oh. Whoop. Can you see this?
Yes, sir.
Whoop. Shit. Can I type so?
Yeah.
All right, come on. Let's start here. So square root.
Okay.
4.
Yep.
Times.
Yep.
Pi. Oh,
yep.
Squared.
Yep.
Hit the bar 2.
Whoa, what? Squared.
You're hitting that key.
Yep, squared, yep.
Right, times 6.8.
Yep.
Right, then you have divide instead of multiply.
Thank you. The iPad's in my way, so it's actually more difficult to do this. Times 6.8 exp6.
Uh-huh.
You got that just like so?
Yep.
Now you're going to hit this key to the power of.
Whoa. Can you point at that key that you just, aha, that's been my problem. Okay. To the power of, yep.
3.
Okay.
Unfortunately, they opened a parenthesis for us, so we have to close it.
Oh.
Nested parentheses. Okay.
Okay. That's a huge deal. Okay.
Yep. Divided by.
Yep.
7 exp
yep.
minus 11.
You just do a normal minus 11?
Unfortunately, that's very evil, but yes. That's
Okay,
not how it
okay.
works in the Casio.
That's what was screwing me up too. Okay, okay.
Divided by
Yep.
6 exp 24.
Yep.
And then close them up.
Okay. Haha, that's the, I didn't realize you had to close the parentheses. That's what's been really.
Always, if they open a parenthesis, we got to close them. That's the rule. Now
Yeah.
let's
Here you
write this down. What should we round it to?
5,400
Units?
seconds.
How many minutes is that?
90.
Seconds to minutes. 1 minute is
1
60
minute,
seconds.
seconds.
You're right. 90 minutes, which is approximately 1.5 hours to go around Earth. Pretty cool, right?
That's friggin' fast.
I know, to go around the entire Earth,
Yeah.
you can't even get to California in an airplane.
Christ.
You have that video to show?
Oh, that's, you know that's coming next, right, Laura?
Yeah.
You were thinking of the one where you remembered that. That was a memorable moment where I showed you guys the real-time orbit around Earth. Okay,
Yeah.
guys, you'll notice I built in a little extra time here. We're pretty much done. That's what you're going to submit. But I want to entertain you for a second and show you something badass. The ISS is really cool. Let's see. If we go up here, we can see some rad pictures. Oh, sorry. Let's go to my internet here. And the ISS is probably a lot of fun to hang out in. First of all, astronauts experience something that's close to zero gravity. It's called microgravity. And that means the astronauts are kind of like in a state of constant free fall. So when you're in the ISS, there's essentially no gravity because you and all the objects are falling. This is a famous, I think this is Chris Hadfield, is this it? He's a famous astronaut that runs a bunch of YouTube pages, and he shows you what everyday life is like aboard the International Space Station. And the pictures are really awesome, right? Like the videos are super cool. They'll just tell you how to do everyday things in space. Like YouTube, make a sandwich on the ISS. So making a sandwich in outer space is way more complicated than making a sandwich on Earth because we take gravity for granted in all the various things it does. So he makes a peanut butter and
Let's talk about space food. In the early days of space exploration, food was mostly squeezed out of tubes and brought up in dehydrated packets. But today, we can have quite a variety of food. There's all sorts of things that we normally consume on Earth that we have here in space. We just need some minor adaptations. In the case of sandwiches, we had to substitute for bread. So we decided to use tortillas. But why? Mostly it's because bread, of course, makes crumbs. When you eat them on Earth, the crumbs fall down to the ground. But here, crumbs are just going to float away. On the other hand, the tortillas that we use are heat treated and specially packaged in an oxygen.
Let's see it make the
Open up the tortilla.
So it's pretty fun watching you try to
Can't rip it. Fortunately, we have space scissors. Squeeze it onto the tortilla carefully.
That's really annoying.
And now a little honey. Hey, I noticed something cool about the honey. Instead of the bubble sitting up at the top, because there's no gravity to make it float up, the bubble is floating in the middle. Envelope of peanut butter and honey is ready to eat.
I love that. His expression is, oh my God, this is fucking terrible. Get me out of here and get me a steak. Now let me show you some other cool things. Anyways, I wanted to tell you about these videos so you can watch. He has how to do everything, how to take a poop in space. Ever think about it? There's no gravity. Things don't work the same. You might need a vacuum. Okay, anyways, one of the other things that I really love about the ISS is the ISS has something called the cupola. So when you have downtime at the ISS, you can basically sit in this beautiful observation window and you can look out. You can just sort of float there. Here's one of our astronauts floating inside the cupola on some leisure time and just looking through the porthole down at Earth. And it's very, very beautiful to do this, a wonderful experience. They have a really wonderful video on YouTube that I like to put on in my house sometimes. It's called Orbit, A Journey Around the Earth in Real Time. They basically took, we decided that it was we calculated 90 minutes around the Earth. And they basically compress a 90-minute journey around Earth. Oh, they don't compress it at all. Look, this video is 1 hour and 32 minutes long. Exactly what you would expect based on our calculations. And they have some cool cheesy space music that we'll mute here, but wait till you see the images, especially the ones, if you have like a really cool 4K television at home, it looks just so amazing. It's very cool to try to look down at Earth and try to figure out what continent you're over. Like here it looks like you're over the Middle East. Like I think that's the Red Sea right there. That's the Nile River, I believe. And in particular, it's very beautiful when they go into the nighttime side. This is what Earth looks like from the nighttime side is really special and magical. You can see all of the cities of Earth sort of marked out by all of the electricity and street lights. You really get the sense that humans are kind of like a cyborg virus that's sort of infesting the surface of planet Earth. And you can see us spread out over the desert here. It's kind of wonderful. Now, obviously, I don't have time to burn an entire hour and a half watching this video with you, but I would strongly recommend you go and kind of put it on in the background while you make a peanut butter and honey tortilla or something like that, and just appreciate what it might be like to be inside the ISS and to float over the Earth in an hour and a half, to sit there in the cupola. That would be a pretty magical experience that not many humans get to do. Okay, cool. So, you know, there's more I could say, but I'm sure you guys have things you'd like to do with your day. How do we feel? Do we feel like we've got that problem down pretty solid? All right. So you all know what you're turning into me, right? You're turning in this as today's lab, right? And you're turning in all those problems that I listed before into me as homework. It's still 5 problems. We just modified it a little bit, okay? Awesome.
Can I see the paper one more time? There's something that I forgot to write down.
Yeah, let's do that. Let me share iPhone. Everything's working good today for once. I don't know if this is the best view, but I'll start here.
Yeah, I just needed one little thing. Now yep, I'm all set now.
How about the rest of you? Pretty good on this?
Good.
Okay. Let's check in on our non-video participants for a second here too. Will, Cameron, Alba, you guys feeling good about this? Will was with us for most of it. Cameron and Alba? Will's got it.
Yeah, I'm good. Yeah, sorry.
Alba gave me a thumbs up. I like it. Hopefully Cameron's doing okay. All right. Cool. Oh, Cameron says all good. Thank you, bud. Thank you so much. Okay, I think that covers us today. I know that was quite a bit. Try not to get too stressed out. This portion is always a little intense, but you're gonna be lean, mean, calculate machines in no time. The homeworks that come after this are a little less intense. So the last 2 homeworks are pretty gnarly. The next ones will involve math, but they won't be quite as crunchy, all right? So I'm gonna stop my recording so that you